Hey everyone, and welcome back to PrepFusion. So in this video, we will try to cover COA completely from basics. Okay, completely from basics uh, to the highest level, whichever is included in the syllabus. Right, whatever topics are included in the syllabus, I will teach everything from scratch, from zero. So even if you don't have any knowledge, no knowledge, right, zero knowledge, still you can watch this lecture and you can get 2 marks. Okay, I will say to you as well for whom this lecture is. So if you are someone who just want to cover the COA, right, in uh, in a comprehensive manner, but don't want to spend too much time, right, don't want to spend around 16 hours, which is there in the comprehensive course, and in the YouTube playlist it's already there. I've covered COA in 16 hours. If you want to if you don't want to spend that much amount of time, if you just want to spend uh, 3 hours, 4 hours, right, then this video is for you. And don't worry, there is no prerequisite, nothing. What is a prerequisite? You should have basic knowledge of computer, right, that you study during your class 10. In class 10 you had a subject, right, computer. Okay, I remember you had a subject. So that knowledge if you have, that's good enough. I will teach everything from basics, and those guys can watch this video. So if you're preparing for gate 2026, or uh, if you don't want to spend too much time in COA, you can watch this video. What will be covered? Machine instructions, addressing modes, ALU, data path, control unit, and instruction pipelining. So all these topics will be covered, but there are few conditions. Before coming into the conditions, you might have a doubt, sir, is this even important? Does gate even ask questions from this particular topic? First of all, it is mentioned in the syllabus, so any day they can ask questions. Second, yes, they have asked questions, although it is on the lower side, but expect it to increase in the future because it is there in the syllabus, right? You don't know when they will ask it. They can frame 2 questions, 3 questions, it's up to them. So I will show you a few questions. This is the first question that was asked in EC 2020. Now we might say, sir, यहाँ पे तो microprocessor लिखा है, this is microprocessor. No, yes, microprocessor is here, but this particular pattern of question, right, can be asked from COA as well. So it's not like it is only from microprocessor. No, because microprocessor is written, many people at that point of time told, okay, this is 8085 microprocessor, not even in the syllabus, maro isko goli. No, this is covered in COA. This was asked in 2020. I'll show you again. 2021 EC. If you don't study COA, you will not be able to solve this question. And all these questions have been solved in this lecture. Again, I will show you. 2024 EC. This was a brilliant question, okay? And this is the last question that I have covered in this lecture, in this one shot. So there are a lot of concepts. Solution is small. Solution is very small here. But if you don't watch the whole lecture, you will not understand a single thing. Okay? So although I have covered everything from basics, you have to promise me that you will watch the whole lecture properly. Okay, that is the promise from your end. Next point. Now, COA is a very big topic according to the syllabus. So it's not like I can compress the whole 16 hours of content in 3 hours. Unfortunately, that is not possible for me. Okay, because if I'm providing any content on YouTube, right, I will provide it to the highest level. So I cannot skip important stuff. Although I have tried to trim down all the irrelevant stuff and try to focus on the only the important part, because this is a one-shot video. Of course, I cannot include every single thing, but with that also this video will go long. Okay, so that's why I decided to make it in 2 parts. This will be the part 1. Sir, what will be covered in part 1? Machine instruction and addressing modes. And don't worry, this is a very important part. Okay, these two cover almost the 50% of the syllabus. So in part 1, almost not even 50, 60% of the syllabus is covered in part 1. 60% of the syllabus is covered. So in this video, 60% is covered. So what about the remaining 40%? Remaining 40% would come with a condition. Only if you watch, like, first you watch this video, okay, if you want to learn COA, and second is you will have to show your support. If you show enough support by liking the video, sharing the video, and by putting down your comments, whatever you felt regarding the lecture, if you understood the lecture, or if you did not understand the lecture, you can let me know. Put your comments, right? I read the comments. So if I see enough demand, enough likes, enough comments, then the part 2 will come. Okay. So in part 1, I have tried to cover whatever have been asked till now. From whatever topics they have asked till now, I have tried to cover those topics: machine instructions and addressing modes. So they have asked from these 2 topics, I have covered it. ALU data path control unit and instruction pipelining. They have not asked from this topic, right? So in the future, if they want, they can. So if you want to future proof yourself, you need the part 2 as well, right? So because they have already asked from these 2 topics, next time they might ask from these topics, right? So yeah, trust me, I have covered everything from basics. So if you don't know anything, only basics of computer knowledge if you have, you can cope up, you can understand it, right? But you need to have patience. This video will be 3.5 hours long. You need to have a bit of patience. Okay. So yeah, with that, let's begin with the first part, that is basics of COA. So let's begin. Basically, this is this broad syllabus that I will explain to you, and then we will begin with the topics. If you go through the GATE EC syllabus, you will see these are the topics that are written into the syllabus: machine instructions, addressing modes, ALU, data path, and control unit, instruction pipelining. So till now they have asked a question from machine instructions, like very basic point. They have asked from addressing modes. They have not asked much anything from ALU, data path, control unit, instruction pipelining. So I'm expecting next time they might ask from these topics. That is the expectation. Now, if you see these are the like COA is broadly divided into 2 parts. One is the organization part, one is the architecture. So GATE syllabus only includes the architecture. Architecture, as the name suggests, it is mainly concerned with the design of the computer, right? What does organization means? Organization basically means how do I organize the different parts, the designs basically. How do I talk to different parts? How do I communicate? So that is a separate thing that is not included in the GATE syllabus. In the GATE syllabus, we have only computer architecture, because COA includes 2 topics, right? Computer organization and architecture. But mainly if you see here, we are only including architecture. The organization part, although I have covered in my full course, but that is for the placement guys. For GATE, you don't need to worry about this. Okay. In next time, if they want, they may certainly include the organization part as well. But for now, these are the topics that you need to study. Okay. So yeah, I will just briefly tell you the definition of computer architecture and organization. No need to remember or anything, just understand intuitively what is happening over here. So if you see, what is architecture? Architecture basically focuses on the functional behavior of the computer system. It involves the design and implementation of various components. So basically, the architecture part focuses on the design. How do I design a particular thing? So if you go into masters, your assignments will be to design a LDO with the input voltage variation of 1 volt to 3 volt, right? So something like that. Similarly here as well. So you need to design a computer that can support, let's say, all the latest games. That means the processor must be very good. So I'm just giving you an example. So you will be given some inputs, you will be given some constraints, and according to those constraints, you will choose your architecture of the system and design your thing, whatever they are asking you to do, right? So yeah, that is what architecture means. What does organization means? Focuses on the structural relationships between the components. So basically, in a particular CPU, sorry, not CPU, in a particular computer, right, there are a lot of things. You know, there is a CPU, there is a RAM, there is a ROM, and don't worry, I will explain what are these things in this lecture only, don't worry. But I'm just like, for the students who already know this, they will have a bit of idea. You have a RAM, ROM, you have hard disks. You know, nowadays it is not even called HDD, it is called SSD, right? It is very faster, much faster. Then you have your external drives, right? Lot of things. Just give me 1 second. Yeah, lot of things actually. So now all these needs to communicate with each other. The communication is done in computer organization. So different things have different responsibilities. Architecture is mainly used for the design phase, and organization basically focuses on the structural relationships between the components. That's it, right? So yeah, so these are the components basically of a digital computer. First is the CPU. So CPU is the central processing unit, which I know that you know because you have been studying this, I think, since class, I think 4 or 5, right? So no need to explain here. So I will just tell you few technical terms. CPU has two units actually. CPU has two units. If you see here, there are two things. One is the ALU, another one is the control unit, right? So ALU control unit is what? Control units directs the flow between the CPU and the memory. So don't worry about all this. What does control unit do? Control unit is the manager and ALU is the engineer. What do I mean by it? So your manager will give you some task, right? Once you will go into the industry or work or somewhere, right? Your manager will give you some task. Manager will give you some task and you will do that. Okay. So similarly here in the CPU, the control unit is the manager. The control unit will give some tasks for the ALU to perform, right? So control unit has all the instructions. It coordinates all the operations, like your manager. Your manager, once you will go into the job, your manager will have multiple people, right? Let's say your manager is there, you are here, right? Let's say here is Neha, here is Rahul, right? So your manager will instruct Neha and Rahul according to their skill sets, because manager knows what Neha can do and what Rahul can do. Correct? Same thing. Control unit will ask a certain unit, some other unit, to perform a particular task, and the control unit exactly knows whom to ask for to perform certain task. So if the control unit, if we have to perform addition or any arithmetic operation, so control unit knows that I need to call ALU. Let's say Neha is very good in what do you call, in the engineering part, right? So basically in the design phase, let's say you have to design a device. So the manager will ask Neha to design the device, and Rahul is very good in marketing. So manager, after designing of the device, manager will then ask Rahul to market the device. So different people, different skill sets, different tasks. Who will manage all those? Control unit. Okay, that is what control unit does. What is ALU? Arithmetic logic units. Simply, as you can see from the name, it performs arithmetic operations, addition, subtractions. Then there are logical operations, comparisons, greater than, less than, and, or, and many more. There are many more. I am not going into all of them, but this is the general structure. Okay. Now, if you see the CPU, first of all, the CPU is actually very dumb. Why it is dumb? Sir, why are you saying dumb? Our smartphones, everything is like very smart. We call them smartphones, supercomputers, smart computers. Why is it dumb? It is dumb Because you will have to instruct every single point to the computer. Otherwise, computer will not do it. Your computer is very lazy. Your computer is very lazy. You know who else is lazy? You. Why you are lazy? Because unless and until I bring a one-shot video, you will not watch it. You will not cover it from the comprehensive course, right? So whatever I will teach here, you just listen to me and you will directly go into the exam hall, right? So similarly, your computer is also very lazy. If unless and until you instruct your computer to do something, it will not do it. If you want to perform add 1 plus 2, you will have to write a instruction set. Okay, there are a lot of things that goes on. So this is called as a high level language. Then it is converted into a low level language, right? Low level language, which is like converted with the help of a compiler, right? And then those low level language, that is actually called as machine level instructions, that are ones and zeros, right? And that will be finally go into the control unit, and your control unit finally will instruct either the ALU or other components to perform their operations, right? So unless and until you instruct your computer to do a certain thing, it will not do it. It's very dumb, right? But you are not dumb, you're smart, right? I will not say you're dumb, you're smart, but you're lazy. Cool. So yeah, that is what our computer is. Now this computer has many components. If you see here, I know you have studied this in childhood, that there is this CPU where CU and ALU are there, and there is this random access memory, RAM. Why is RAM required now? Now your CPU is very fast. It can perform operations very fast. You are also very fast. Okay, you're lazy, but given that I instruct you to do something, you will do it, right? If I don't instruct you to do anything, you'll not do anything by yourself, right? You'll not study. Once I bring the one shot, you will study. Now your CPU is very fast, but your CPU has very little memory. Again, I will give the example little memory as me. Okay, my memory is very weak. My memory is very weak. So what do? I write most things, or what do? I store somewhere it, right? Let's say I remember that, okay, I have to wash my clothes or do something, right? I have to get and buy a particular thing from market. So I will set a reminder or write somewhere. So similarly, CPU, although it's very fast, but it needs a bit of storage to store the currently processed data. Let's say I am adding two numbers. It is, in this case, it is very easy. It is 3, right? But what happens if I add 101 and 101 again, right? So what happens? This is 1 plus 1, that is 0 actually, right? Because 1 is carried. 1 is carried, and then this 1 comes here. Then 1 plus 0 plus 0, that is 1 only, and then 1 plus 1 again 0, and 1 is carried. Okay, let's say this register, this particular register can only store 3 bits of information. So what is the sum of these two numbers? It is simply 0, 1, 0. But is it correct? No, it is not completely correct, right? Because this addition had also a carry of 1. So this carry will be stored somewhere. Okay, so all this information during performing an operation needs to be stored somewhere. So that is stored in the random access memory. Now few smart students will come to me that, sir, for these kind of things we have cache memory, and I will say you're not wrong, you're correct. But this cache memory came later. First there was RAM. Cache memory was there, but the size of the cache memory was much smaller. Now it has become much larger. There are multiple reasons to it, but we don't have to get into that right now. Okay, Cache memory is even faster than RAM. Okay, but don't worry about this right now, just worry about RAM. Now you might say, sir, why are you saying RAM here? We have hard disks. Why don't we store all the data in the hard disk? You might have the doubt. Why don't we store all the data in the hard disk? So there is a reason. What is the reason? The reason is very simple. That your RAM will always be accessible to the CPU. Your hard disk may not be accessible to the CPU. Correct. So you have, it is you, right? This one is you, and you have F friend circle, right? Let's say this is friend F1, this friend F2, and you know, like, you will have a close friend and not so close friend. So if you are in a problem, let's say you need to copy the assignments or you need the assignments of lab or something, right? Whom will you call first? You'll call F1 first, correct? Because F1 is more close to you. F1 is more accessible to you. So same thing is happening over here. RAM is there for a reason. You're correct. We could have used secondary memory. The point one is secondary memory like hard disk, like your 1 TB external hard disk. They are very slow. Yes, they are very slow. RAM is very fast. That is the point one. And point two is they are not always accessible. So there are more reasons. I'm not getting into them right now, but these are the main two reasons why we use a special memory, RAM, to store all the data or the results of the current process. So whatever process currently your CPU or laptop is running, we need to store the data, and that data is stored in the RAM. Okay, so RAM is faster. RAM is faster than hard disk. Why it has to be faster? Because your CPU is very fast. Your CPU, if you remember, can process millions of instructions every second. If you remember, there was a post from Apple, right? They can process billions of instructions in a second, billions. So although your computer is very dumb, but it can process billions of instructions per second. So if you are able to provide billions of instructions, it will do that in a second. So in that way, it is very fast, but you will have to instruct it, right? So that is the thing over here. That's why, as it does the processing very fast, we need a fast storage solution as well. Otherwise, all this data will not be able to store it fast enough, and this data will be lost, and this data may not be relevant anymore. So let's say I have to add these two numbers, and then I have to add the next number, that is 0, 1, 1, right? So what do I have to do? So basically, these two additions, this has to be stored in a particular register, right, in the RAM, and this carry bit also has to be stored. Although the ALU has performed this addition and it wants to perform the next addition, that is the result plus this, but this data was not stored in the RAM, and the RAM was not fast enough to provide me the data, I was not able to do the addition. I was basically bottlenecked. Due to what? Due to slow storage speed. So that's why our RAM must be very fast, because our CPU is very fast. Because the CPU is very fast, RAM has to be very fast. Okay. So yeah, that was like, although this is not in the syllabus per se, but you should know all these things. And these kind of things will help build intuitions. Basically, understand computers even better. So yeah, that is what memory is. Main memory, we have main memory, primary. These are called primary memory, also called as main memory. Random access memory, it is temporary. Why it is called temporary? As soon as you will turn off your computer, it will go away. So that's why it is also called as volatile storage. So it is only able to retrieve the data when the CPU or your machine is on. So if your power is off, the data will be gone, data will be lost. So data, it is very fast, but there are obviously advantages and disadvantages. of everything. Okay, so data will be lost as soon as you will close your computer or power off your computer. ROM is read-only memory. It is non-volatile. Data will not be lost. Okay, even if you power off your computer, data will not be lost. Now, why is ROM used, and what is the difference between RAM and ROM? So, random access memory basically means I can access my memory any point of time in any point of index. What does it mean? So, let's say I will explain. Don't worry, all this later on. For the students who already know this, let's say I have data at 101 address, 102 address. What does this mean? So basically, right, you stay in a home, so your home number will be some house number 7, right? Or let's say you have a pin code. My college pin code was 70032, correct? Jadavpur University. So, and then there will be a pin code 70031, 7003233, right? Everything which has an address has a particular code. Same will be applied here as well. So each particular memory cell, these are called as cell, and I will come to them, don't worry, later on. They will have a code. All of them will have a code, each of them. This will be the 101th cell, this will be the 102 cell, this will be 103rd cell, like this, and so on. So in random access memory, what happens? The name random access basically means at any point of time I can access, let's say, 109 location, and the next second I can access 101 location. It's not like I have to access sequentially. That's why it is very fast, because if the CPU wants, it can access 109 location. Maybe the information that is stored in the RAM that is required by the CPU is stored in 109. So I can directly go and access 109. What is the difference in sequential memory? In sequential memory, if let's say I had to access 109 location, right? First you will have to go to 101, 102, 103, 104, 105, 106, 107, 108, 109. So I hope you can understand, right? It will take us more time. Now you might say, sir, why do we use sequential? You're correct. Nowadays the use of sequential is getting reduced day by day. Before, why it was used? Because this particular thing, to develop this, right, it is very costly. It is very costly, and if you know your RAM is 8 gigabytes, 8 GB, 16 GB, your storage is 1 TB, right? So of course, I hope you understand the fact that it is very costly. That's why previously it was not done, but slowly technology is developing, so we are moving towards that. Like our own personal storage devices are also following the random access. Example, SSD. Cool. Now what is ROM, sir? ROM is nothing but it just contains, it is a special type of memory that contains very essential instructions. Okay, so now you say, what do you mean by essential instructions? So you have a laptop. The moment you press the power button on your laptop, what happens? You press this is the power button of your laptop, right? What happens? The moment you press the power button of your laptop, you see your brand screen, right? If it's HP, you'll see HP. If it's Asus, it will be Asus. It is Apple. If it's Apple, it will be Apple. And then it will load Windows. So the moment you press the power button, there are certain set of instructions. I have told you, right? The starting of this lecture, that your CPU laptop is very dumb. It needs instructions. So there are certain set of permanent instructions that are generic, because everyone will press the power button, right? Everyone will press the power button, right? So the turning on process is very generic. So that's why these are hard coded. You cannot delete them, and these needs to be always there. That's why it is non-volatile, because we are turning off the computer, right? I will turn on the computer, and those instructions need to be present in the memory. Okay, otherwise your computer will not turn on. So I will tell you a very interesting fact. Do you know why is the sign of your power button like this? Do you know this? I will tell you. I got to know this from my friend in the office. he told me that if you see this, look at this carefully, this is a combination of 1 and 0. So this part is 0 and this part is 1, and your computer is also a combination of 1 and 0. So everywhere you see your remote, your CPU, your laptop, power button, the symbol is this. The reason is this is 1 and this is 0, because your computer only understands 1 and 0. 1 means on and 0 means off. Whatever you have studied in digital, that is what we do actually. Okay, so this is a very interesting fact, although not important for exam point of view, but yeah, it's good to know, have a bit of curiosity. So in short, your RAM will store all the current instructions that the CPU is running. So if the CPU, let's say, is running Google Chrome, right? I'm opening Google Chrome. So all the data related to Google Chrome or the program memory, right, it will be stored in the RAM. ROM will consist of the inbuilt instructions that generally we don't change them. Okay, we don't change them, but you can. There are ways, but for our purposes, you will say these are inbuilt instructions that were that was stored during designing of the CPU or the during design phase. Inbuilt instructions during designing. Right? Okay. And secondary storage, very simple. It is used for long-term storage, hard disk, SSD. You already know. Not explaining this. So yeah, let's solve a very interesting question. Whatever you have learned till now, let's solve a question. Right? Which of the following elements are part of computer architecture? Addressing modes, yes, it is part of computer architecture. CPU design, yes, of course, we have seen the syllabus, right? Instruction set, data format, yes. Secondary memory operating system, is it? No. Why? Secondary memory, right, is outside the computer. That's a user choice, correct? An operating system, again, the user choice. I can install Windows, I can install Linux, I can install any other operating system. So the way I communicate with the device, that's up to me. Addressing modes, CPU design, CPU inside the laptop. These are very fixed things which are already designed during the definition phase of the device, right? So these are primary things. These are basically computer architecture. So in this case, answer will be option 1 and 2. So these are the parts of computer architecture. Okay. So as I was explaining previously, what is your memory? So memory, so your CPU can only understand ones and zeros, and we need to store these ones and zeros somewhere, right? So these ones and zeros are stored in the form of rows and columns, and this will come up, and GATE have asked question from this topic. Okay. So CPU can only understand ones and zeros. So how do I explain this? I have already told you, right? Each particular location will have a number, correct? You know, pin code, right? I have already explained pin code. Similarly, this is the pin code. For this is a cell 1. This is called as a cell 1. Okay, these are called as cell. This is cell 1, this is cell 2, and this is the pin code of this cell. Similarly, someone walks into your home. So in your home, there will be a, if you are very rich, there will be a living room, there will be a kitchen, correct? So your home will have a house number. Let's say house number 7. So first I will have to get into house number 7, and after getting into house number 7, if I want to watch a sport, cricket, right, then I have to enter living room, correct? Then I have to enter living room. Similarly, first I have to enter, if I want to access this particular cell, how will I access it? So first I will access the address 0, then inside that address 0 I will access address 1. Why 1? Because this is, we always start from 0, right? So address 0, then inside this I have two cells, right? So they will be marked as byte 0 and byte 1. So this will be the 1 byte. Cool. So yeah, now like you might have a bit of confusion here. So there are byte addresses, there are memory addresses. Which one shall I choose? Don't worry about it. Don't worry. We'll get into each of them. But for now, you just understand this thing, that your memory will be uh, basically your memory will be displayed in the form of rows and columns. And generally what happens, we have a single row only. Generally that is the structure, but there can be multiple rows as well. I will come to that. Don't worry about it. But for now you need to understand that what is 8 bits. 8 bits will be 1 byte, because of course uh, your 1 bit has very less information, 1 and 0. That is not enough for us. So that's why we store data in chunks of bytes. And this particular chunk can also change. We can store in chunks of word as well. I will come to that. So these are your input and output devices, mouse, all these things. So I don't need to explain all this. This will be covered in organization. That is not our purpose. Okay. Now this one is actually pretty important. Okay. Although this comes under the communication, but understanding this is very important. And this also, this system buses will also be defined in the architecture part only. Okay. Very, very important. Listen to me very, very carefully here. So what are system buses? So you have your, I have already told you, right? You have your control unit. Inside the ALU you have a control unit, you have your ALU. Sorry, inside the CPU you have your control unit, you have the ALU, then you have your memory, and then you have a secondary memory. Not getting into that right now. So your ALU needs to talk with, sorry, your CIP's control unit needs to talk with ALU. So your control unit is the manager, right? And your ALU is the engineer. And both of them need to be in a common platform to discuss. It can be like, Microsoft Teams, right? It's a very famous corporate solution that is being used by many companies, where people can chat, basically talk. Obviously, not just time pass, do the work for work purpose, right? For the work purpose. So your manager needs to talk with engineer, your control unit needs to talk with ALU. How will it talk? Through the system buses. Why the name bus? Your bus, what does your bus do? Real life, your bus takes you from a particular point A to point B. And the same thing will be done here as well. Your system bus will take the data from point A to point B. Your system bus will take the instruction from control unit to ALU. Your system bus will take the data from ALU to memory. That is the task of system bus. Now there are broadly 3 kinds of system bus. There can be many as well, many more as well, but mainly there are 3 kinds of system bus. And you will say, sir, do I have to remember all this? Trust me, once you will read all this, right, you will not remember this. It will be automatically there in your brain, because you're engineer. You're not dumb like computer. So now so let's take a very basic example. So if your control unit needs to send some instructions, right? Let's say perform addition or send some control signals, because your control unit always sends the control signals. Let's say I want to do this addition 1, 2. So in this, what is my instruction? This is my instruction. 1 and 2 my operands, where the data is stored. So what will happen in this case? A lot of things will happen. So this addition is a instruction which consists of multiple control signals. Right? To perform additions, your CPU will break it down into even simpler instructions. Like what? Let's say you want to perform this 101 011. Will you perform it directly? No. First you will add the LSB bit, then after that you will take the carry and then you will add, right? That's how you perform the addition. your CPU also does the same. It performs the addition in a slow manner. Okay, so what will happen here is that it will perform the addition one by one. So that's why this addition is a accumulation of lot of control signals which will be sent in the control bus. This data will be, so I need to perform addition of 1 and 2. This data will be sent in the data bus as the name suggests, and the address bus will be what? Address bus will contain the address of the data or the instructions depending on whatever it is. So of course 1 and 2, it's not like it will come from air, right? It will not come from the air, heaven. It will be stored somewhere. Let's say this 1 was stored in the location 101 address, and your 2 was stored in the location 201 address. So this 101 and 201 will be shared in the address bus, and this 1 and 2 will be shared in the data bus. Basically it will get the address, and from that it will take the data and it will share to the ALU, and the ALU will perform the operation. Lot of things I do agree, but once, like after this whole one shot, you will understand everything, don't worry. Now few things, your address bus will be unidirectional. Why? Because if you are sending the address, that means you want to get access to certain data, read or write the data, right? So the CPU will always send the address lines. Your manager will always tell you whom to contact, what task to do. So the and whom to contact, right? That whom to contact would be similar to address bus. So basically your CPU will tell which particular location I want to access. So that's why it is unidirectional. Your secondary memory will not tell, okay, oh, hey man, CPU, go and access the location 2000. I'm saying no. CPU is the manager, right? Do you tell your manager to like do this or do that? No. CPU is the manager. So your CPU, your manager will tell you what to do. You will not tell what to do to your manager, correct? So yeah. Now what about data bus? Data bus will be bidirectional. Now you will say, why it is bidirectional? This also should be unidirectional. No. What will happen here is either you can read the data, right? Basically store the data in your local memory, or write the data after some operation. Let's say I need the data, right? I need 1, 2 in location 101 and 201 from location 101 and 201. So in this case, I am taking the data from the outside world, and then after performing the addition, that is 3, I will store it somewhere. Then I'm sending the data. So storing it, sending the data is actually called as write operation, and reading it, like basically retrieving the data, is actually called as read operation. Okay, got it? Control bus, I have yeah, so these two are called as signals, reading and writing. These are called as control signals. Okay, and the data that is to be written or read back is actually called as is actually done in the data bus. Okay, this is bidirectional because data can be read or written. Control bus, mostly it is unidirectional. Sometimes it can be bidirectional as well, because you might have a doubt, sir, you just told your CPU is manager, so CPU will send all the control signals. Okay, in case of address, it is very simple, right? Because address, either you'll read from that address or write to that address. There is no other possibility. Your outside world will never have access to the inside memory or CPU address. That is never possible. That's why this is unidirectional. But sometimes what happens is some control signals we send to the control unit as well. That's why it is bidirectional. But don't worry, no need to get into that right now. Just understand this much. This is enough. Okay, to solve a question. And from this particular topic, APYQ has been asked recently, 2021. Okay, before that we will solve this first. The minimum number of address lines required for the computer to function properly, this should be 4. Okay, I don't have the keyboard, just give me 1 second. Yeah. For the computer to function properly, So if you see, there are 8 cells, and if my CPU want to access all these cells, how will I access? So what do they mean by address lines? So I've already told you, right? Your address, there will be address bus through which the CPU will send the address or location of the data that is required. So this is my secondary memory. How many locations I have? If you see, I have total 8. So basically it is 3-bit, right? Total 8 address locations. Total 8 address locations. Now, I will tell you a very interesting fact. Your address bus is basically combination of multiple lines. What are these lines? These lines basically will send either 1 or 0. In each line, you will send a signal 1 and 0. And what do these signals represent? You guessed it right. These signals represent the address for a particular data that you want to access. Let's say I want to access 011. So let's say this is the address line 0, L1, L2. So L0 will be the LSB, right? L0 will be 1, L1 will be 1, and L2 would be 0. And there will be a basic mux, right? I hope you know what is a basic mux. It's just a it is just like a mux, and it is actually a mux only. Correct? So your mux will have select lines, and all the data are actually connected here. Okay, this is I0, I1, I2. So according to your select lines, this is L2, L1, L0. So whichever one I will select, I will choose that. So in this case, I will select 011. So 011 is nothing but 3. So the output of this mux will be I3. So whatever data is stored in I3, that will be transferred. It is just like that. It is just like select lines. So your address lines is nothing but just like your select lines, because it is, the structure is similar to a mux. So if I have 3-bit address, 3-bit address, how many lines do I need? How many lines do I need? 3 lines. How many select lines do I need if I have a 8x1 multiplexer? 3, right? Similarly here also 3, because there are 8 different addresses. So if there are 8 different locations of address, how many address lines you will need? 3. So if I have 4, not 4, let's say 16 different addresses, how many select lines you will need? 4, right? Correct? You need 4. Why? Because how many bits it is? Like, what is the maximum number? You have 16, right? So to represent 16, it will be from 0 to 15. So this 15 is represented by 4 bits. So each bit will be each address line. So you will need 4 lines, 4 address lines. Okay. Of course, there is a formula. There is, of course, everything has a formula. Not want to. I know. If you know already this formula, that's great. But I don't want to focus too much on the formula. I want to focus on the concept. Okay. So you can use, right? You can use the formula. So let's say if I have 32 bits of address length, then what will be the number of select lines? It will be simply log base 2 of 32. That is nothing but 5. Basically, if your total number of memory locations or total number of address bits is in the form of 2 raised to power m, so your number of address lines will be simply m, right? But what if it is not in the form of 2 raised to power m? What if your number of addresses is 30? Number of memory locations is 30. Then how will you solve it? You can't store half a bit, right? That is not possible. Either you can store a bit or you cannot. Like basically you can either store a line or you cannot, right? It's not like if I need half, so if I need 30 address bits, so you will do log base 2 of 32, and that will be what I can exactly calculate the value. Log base 2 of 32, 30 of log base 2, that would be 4.9. And you will say, sir, I will need 4.9 bits. It does not work like that. Correct? I need 4.9 lines. No, because your line is a fundamental quantity, just like bits, just like electrons. Can you break down a single electron? No. So either you will need a line or you don't need a line, right? So either it will be 4 or 5. Which one it will be? It will be 5. Why? If it was 4, what is the maximum number of addresses that your architecture can support, CPU can support? It is 2 raised to power 4, that is 16 unique addresses. We solved here, right? We just solved here 16 unique addresses. But here, if you see, I need to store 30 addresses, but you are saying if I use 4 address lines, I can only store 16 addresses. So I will need 5 address lines. So this will be 2 raised to power 5, basically 32 address lines. Now you might have a doubt, sir, few locations are getting wasted. Like you only need to store till 30, right? That is 0 till 29. So the remaining is what? 30, 31 are getting wasted. Okay, so how do I calculate the greatest number and lowest number? So this also is a very like big doubt. I do understand it. So let's say I have 32 numbers. Let's say two numbers, 4 and 5. How many total numbers are there between 4 and 5, including both 4 and 5? It is what? 2. You can see it, 2, right? So if I say 30 till 60, how many numbers are there between 30 and 60, including both 30 and 60? You will say it is 30. No, it is what? It is 31. So there is a very simple thing that we do. So it is the upper limit minus the lower limit plus 1. Okay, so this will be 31 numbers. So that's how we calculate it, and this will be utilized in a lot of places. So make sure you understand this method. Okay, let's come back to our topic. So yeah, these numbers will be wasted. 30 and 31 locations will be wasted because we will not use it, but that's fine. But at least your system can support it. Otherwise, if you choose 4, your system will not even support it. So that's why this sign is there. This sign basically tells us that choose the upper limit. If you have a floating point number, let's say 2.8, you will choose the upper limit. That is 3. Upper limit integer. So this question came in GATE 2020 easy. So if I am telling you some concept, that means either it has been asked or it will be asked in the future. There is a very high chance of getting asked. I'm not just coming here without research. GATE has asked question from EC and they will ask questions from this particular topic. And although most educators will say this is a 8085 question because they have not even read the question, okay, and it's already in the syllabus, they will say it is out of syllabus. No, it is not out of syllabus. It is not. Trust me, it is not out of syllabus. So yeah, in 8085 microprocessor, the number of address lines required to access 16 kilobyte memory bank. Now, what is 16 kilobyte? I've already told you that 1 byte is equals to what? 1 byte is equals to 8 bits. Kilo, what is kilo? I hope you know what is kilo, right? It is 10 raised to power 3. 10 raised to power 3 is roughly equals to 2 raised to power 10. What is 2 raised to power 10? It is 1024. Actually, kilo, right, is not 10 raised to power 3. Actually, kilo is 2 raised to power 10 in computer world. In digital world, kilo is actually 2 raised to power 10. It is not 10 raised to power 3. But as they are very close, we roughly say they are equal. Okay, but actually in computer world, you will always remember your kilo will be 2 raised to power 10. So what is the number of address lines if your memory bank has this much amount of addresses, right? 16 kilobyte. So basically, if I will just break it down into a very simple case. If I have a 2 byte memory bank, what does it mean? I have already told you, right? Your memory is stored in the form of rows and columns. If nothing is mentioned, you will assume one column. If there are 2 columns, I will come to that. That is a advanced topic. I will come to that. So one column, 2 byte memory. What does 2 byte memory means? So basically, uh, how many different memory locations are there? Okay, how many different memory locations are there? Now, one more thing, that unless and until nothing is mentioned, you will assume that your memory is byte addressable. Byte addressable. I've already told you this previously here. What have I told you? That data is stored in the form of bytes. Where did it go? Yeah. Data is generally stored in the form of bytes by default. So one particular row is called a cell, and each cell will store 1 byte of data. Let's say my memory has 2 bytes. So each cell will store 2 bytes of data. 1 byte here, 1 byte here. Total how many bytes? 2 bytes. Understood? Total how many bytes? 2 bytes. If my memory is 4 bytes, it will store 4 bytes of data. This I am telling you for a byte addressable. If nothing is mentioned, it will be byte addressable. What does byte addressable means? Each cell will be 1 byte. Okay. I will come to the advanced topic later. Don't worry. For now, you understand each cell is 1 byte. So if I have a 16 kilobyte memory, how many different rows I will have? Basically, how many different addresses I will have? In this case, what will be this first cell called? It will be the cell 0 and this will be the cell 1. If I have a 4 byte memory, 1 byte over here, 1 byte over here, this will be called as the cell 2, this will be called as the cell 3. So how many bits do I need here? How many address lines? It will be log base 2 of 3. It is what? It is the upper limit basically. So there are 4 different locations, that is 2. So I will need 2 bits, 2 different address lines. Now let's come back to our question. My memory is byte addressable. The total memory size is 16 kilobytes. So how many different bytes I have? 16 kilo. The total number of bytes or total number of memory locations is 16 kilo. If I had 2 memory locations, I needed 1 address line. If I had 4 memory locations, I needed log base 2 of 4 address lines. If I have 16 kilo bytes of memory, how many address lines I will need? Log base 2 of 16 kilo, that is 2 raised to power 10 address lines. Don't remember the formula, understand the concept. So this will be log base 2, 2 raised to power 4 into 2 raised to power 10, that is 2 raised to power 14. So 14 can go outside, this will be simply 14 bits or address lines. So I will need 14 address lines. The answer of this question would be 14. Okay. So if the byte addressable part, I think it was clear, and there are other advanced things that will come to, but for now I just wanted to solve a question to let you know that these things are asked in the examination and they are important. Okay. Yeah, so let's now discuss about few more things. One is this cache memory, again not important, just wanted to give you an overview. So between main memory and CPU, right, RAM and CPU, there is an intermediate memory that is even faster. Okay, so don't worry about it, not in your syllabus, but that's the structure basically. This is a structure. Okay, because your CPU sometimes directly does not want to talk with main memory. It needs to perform even faster operation. Sometimes what happens is the CPU needs a particular data multiple times, just like you, right? So you have your table setup, right, in which you have pen, laptop, your recently used study materials like copy, recently studied books. So you keep them by your side. CPU is also like that. So CPU would keep the things that it needs multiple times, and it knows it will need it in the future in the cache memory, which is even faster. So the moment CPU wants a particular data, it will not go into the main memory, which is slower than cache memory. Yes, you are correct. Main memory is faster than secondary memory. That is correct. But sometimes CPU wants even faster operation. For that particular reason, it needs cache memory. Okay, that is the only thing that you need to understand. Nothing else. Okay, that's it. So here is the basically complete flow. What happens during read operation? What happens during write operation? So during read operation, the data goes from memory to CPU, right? So what happens during read operation? The data is already in main memory, the current instructions and all the operands. Now it will need to go into the CPU. Basically, if I write at 1 comma 2, so this 1 comma 2, this data is in the main memory currently. These two data needs to go into the CPU to perform the addition, right? Now you might say, sir, then why don't we store everything in the CPU? No, right? Because there are gigabytes of data, and CPU does not have that much amount of storage. CPU has only few kilobytes or megabytes of data. Sorry, megabytes of storage. That those are called as CPU registers. Those are very special purpose storage, very fast. So we copy we copy these data into that register. That copying is done here. Okay. So what happens? The CPU sends address of memory location through the address bus. So first we send the address in the main memory. It will be stored somewhere in the 100 location. So we will send this 100 location address in the address bus. I'm talking this for read. Then what happens? The control unit sends the read signal through the control bus. Through the control bus, the control unit sends the read signal. Then the CPU finally reads the data. Okay, these are the three process. And how does it read? The data is now flowing back into the data bus. So it is coming back from main memory to data bus. So what is happening? First I sent the 100 address in the address bus. Then I send the control signal read, and then finally after it receives the control signal, the main memory sends the data in the data bus. There is 1 and 2. Let's say 1 only. 1 is stored in location 100, and in location 101 2 is stored. So then after this, if I send address 10101, after this data 2 would be sent. Okay, that is the proper operation. A similar operation would be done for write. I'm not explaining it, you can read this. Okay, so these are the things that happens. You can go and read this and understand it even better. I have already explained these things. Okay, so as I was explaining that there are few registers. These registers are inside the CPU, because CPU, of course, before performing any arithmetic operation, it needs to store the data, and these registers are very fast. So we copy the data from the memory to the registers, and then we perform the operations. Okay, so I know it's a bit of confusion that why are there so many storage levels, why are there so many things. All these are there just to make our lives easier. So these architectures are there to make your lives easier. You also have your stuff very organized, although I am not very organized, but I hope you are. So you will have your copy and everything, right, in this particular table. Your bed will be also organized, so everything is organized. So there are reason for organization, so there is also reason for all this. Okay, although I have explained it and it might feel a bit overwhelming, but there are a proper reason to do like this. Okay, if we have found a better way, then obviously this system will be improved. Okay, so we have these registers. These are called as CPU registers. So there are many kinds of registers. These are the few important ones. Okay, these are the few important ones which I will explain, and they have asked a question from this particular thing, stack pointer. Okay, they have asked a question from stack pointer. So it's very important actually. So whatever I'm teaching you in this initial portion, they've asked a question. So I'm expecting next time they will ask bit advanced, like what do you say, the instruction pipelining and stuff, right? They are yet to ask from it, but they can. If they want, they certainly can ask from it. Okay. So yeah, I'll just briefly go through all of them. So general purpose registers are used for temporary storage during computations. So let's say I want to perform add 1 2, so I need to store 1 2. Those will be stored in the general purpose register. Special purpose registers are very special. Okay, they store a particular kind of data. First one is this accumulator. So do you have to understand and remember all these names? Yes, but these will be not that difficult for you to remember. It will be very simple. You can just see the name and you will understand. Accumulator is what? It stores the immediate results received from the ALU. So let's say if I am performing add 1 comma 2, so the accumulator will store what? It will store 3, the immediate result of the operation performed by ALU. What does the program counter hold? Program counter holds the address of the next instruction to execute, because we always need to know what will the CPU do next, otherwise it will just be stuck in a loop. So program counter holds the next address of the next instruction. Okay, the instruction. It is not the operand or anything. It is the address of the next instruction that we need to hold. Right? So instruction is stored somewhere. Everything is stored somewhere. Instruction is also stored. So after, let's say, add instruction is stored in the location 101, and then 102, the subtract instruction is stored. So program counter, if I am currently performing addition, the next, generally what happens, generally the next instruction is just sequential, right? So if currently the PC value is 101, as soon as the ALU will start performing addition operation, the PC value will increment by 1. So this will become 102. Now there are certain things called as branches, due to which the program counter can change, which are called as addressing modes and stuff. Don't worry, we will come to that. We'll come to those later on. For now, simple thing, program counter increments by 1. Okay, we'll come to that point when it will not increment. So just keep this in your mind that this will not always happen. It will not increment by 1. Sometimes it will be a different value, but for now you understand it like it only increments by 1. Cool. So this add operation is currently getting performed and the program counter value has been incremented by 1. So it has now become 102. So as soon as the addition operation will be performed, the result will be stored in the accumulator, and your CPU will now go into the program counter to see what is the next instruction. So CPU goes into the program counter, it sees the next instruction address is 102, so we will go into 102 and your control unit will send the control signals to perform subtraction now. Okay, so that's the sequence basically. I'm just giving you an overview. And next is the instruction register. So instruction register stores the current instruction that is being executed, like add, like subtract. Okay, so these are few things that you need to understand. Then we have stack pointer. So if you have not studied already, I will just briefly tell you what is a stack. Stack, as the name suggests, is basically a stack of anything. In this case, it is a stack of data. If I say I have a stack of books, so let's say book B1, then I have B2, then I have B3, like this, right? And this is my basket. If I say to you, I want to read book B1, can you take the book B1 without taking out B3 and B2? No, in this particular architecture, you cannot, because it is a box, right? So first you will have to remove B3, then you will have to remove B2, and then only you can read B1. You can get to B1. So that is exactly how a stack works. So stack works in the structure last in first out. What does last in first out means? Last in first out basically means that what was the last object that was into the stack? B3. So next time, once you next time, if you want to pop anything out of the stack, what needs to be out first? B3. So whatever was the last in, that is the first out. That's why LIFO, last in first out, right? So we have a similar thing called as FIFO, where it is first in first out. Don't worry about it, not in the syllabus. Just I'm giving you a bit of comparison. Got it? So if I want to store any data into the stack, that operation is actually called as push operation, pushing into the stack. If I want to get anything out of the stack, that operation is actually called as pop operation, popping out of the stack. Okay, so if I say I want if I say pop B3, that basically means this B3 will be popped out of the stack, this B3 won't be there. If I say push B7, that means push the book B7 into the stack. Got it? So these are a few things that you must know. Then there is flag registers, or also called as program status word. Basically, whenever you perform any operation in the ALU, there will be some flags like zero flag, like carry flag. I'm just giving you an example. So if you are performing addition operation and it's a 2-bit addition, right? 1 plus 2. It is 3. So this can be stored in 2 bits. But let's say if I want to do 1 plus 3, what is it? It is 4, which is a 3-bit number. So this is called as a carry. So whenever we are performing an operation, we will store the immediate result in the accumulator. But what about this carry? So this carry will be stored in the flag register. So this flag register will be a combination of multiple bits. One of the bits will be carry, which will be either 0 or 1 depending on the result. So in this case it will be 1. Then we have 0 flag. If the addition was 0, then 0 flag also will be high, otherwise it will be low, just like that. Okay, there are multiple things. Then we have memory address register. It stores the memory address for data instructions. Memory data register, it temporarily holds the data that is being transferred to or from the memory. Okay, as the name suggests, very simple, straightforward. Okay, if you want to know more about them, have a read. Pause the video, have a read here. Pause the video, have a read here for the program counter. Already have explained, but if you want to understand more about them, you can read all this. These are there in the notes. You can always read all this and understand more about them. Already have explained you, right? Just one thing. So whenever we push something into the stack, so there is a thing called as stack pointer. Okay. So here also I have also told you that program counter, as soon as the current instruction, as soon as the ALU will perform the current instruction, the program counter value will increment by 1. For our purpose, for now it will increment by 1. So similar thing happens in the stack pointer. Stack pointer always points to the top of the stack. So let's say this location was 101 or 100. This location will be 101, this location will be 102, something like that, right? So first B1 book was in the stack, then B2, then B3. Your stack pointer always points to the top of the stack. So this is the top of the stack, right? So what is the location that my stack pointer is currently pointing at? It is 102. If let's say I push a new book, B4, what will happen? B4 will be pushed here. B4 will now become the top of the stack, and your stack pointer will increment by 1. So it will be SP plus 1, that is 103. So that is what will happen to your B4. Stack pointer will increment by 1. So whenever you push an item, your stack pointer always will be incremented by 1. Whenever you pop an item, what will happen to your stack pointer? It will always be decremented by 1. So if let's say I want to pop from the stack, right? Pop. If I am saying pop, that basically means pop the top of the stack. So B4 will be popped out of the stack. Now the stack will contain only the top of the stack will be now B3. So what will happen? Your stack pointer will be reduced by 1. So 103 will now become 102. So whenever you are performing a pop operation, stack pointer will be reduced by 1. Whenever you are performing a push operation, stack pointer will be incremented by 1. Very simple and easy to understand, right? So if you want to read more about flag registers, have a read. Okay, so this is the flag register where each elements define multiple things. Okay, you can read this, pause the video, like this is taken from a website. You can read, understand it, but not super important, but you can have a read and understand what does each flag registers do. Again, address registers and data registers already discussed, not discussing it again. Okay, so there are few architectures that you must understand, otherwise it will be very difficult for you to proceed in the question, because every information will not be given to you. And don't worry, once you get the hang of it, you will understand everything. Don't worry about it, right? So first one is the accumulator based architecture. So what happens in an accumulator based architecture? The ALU uses single accumulator registers as one of its input for operations. So basically what happens is ALU uses, so if I say add 3, you will say, are you joking? Are you joking, sir? You are saying add 3, but you are not saying me add 3 with what, right? There will be some number, right? 3, 1 and stuff. I will say to you, no, I am not joking. I am not joking to you. I will only say add 3 to CPU and it will perform the addition. It will perform the addition with what? It will perform the addition with the data that is stored in the accumulator register. So let's say accumulator has currently stored as 1. Accumulator is also a register only. It is a special kind of register where the result is stored, but it is a register only. So if currently the data stored in accumulator is 1, and if I ask my CPU to perform this operation add 3, what will be the result? It will be 3 plus 1. Where will it be stored? Again, it will be stored in the accumulator. So the previous data will be overwritten and the new data will be 4. So this is my accumulator based architecture. Got it? So basically in accumulator based architecture, we only provide one operand. The other input is already there in the accumulator. The graph, I think, do we have the graph? Okay. We don't have the graph, but you get the point, right? ALU has 2 inputs. Okay. What is the second one? Second one is very simple. Register based architecture. The ALU directly operates on the data stored in the general purpose register. So I have already told you CPU has some general purpose register, let's say R1, R2, R3, and each register can store 8 bits of data. Okay. Now this architecture can change. Each register may store 2 bytes of data. Each register may store 4 bytes of data. That can change depending on the architecture. But if nothing is mentioned, by default you will assume each register is storing 1 byte of data. Otherwise it will be mentioned in the question. How? I will tell you later on. Don't worry about it. So if I say add R1, R2, then what it will do? Whatever is the data stored in R1, whatever is the data stored in R2. So let's assume that in register R1 currently the data stored is 3. In register R2 the data that is stored is 4. So it will be 3 plus 4, that will be 7, and 7 will be stored in accumulator register. Now you might say, sir, what is the advantage of this particular kind of architecture? What is the advantage of this particular architecture? So every architecture has their own advantages and disadvantages. What is the advantage here? I don't need to provide an extra instruction, right, that add the result of the accumulator. That is already inbuilt in this architecture. So my program memory is lesser. It will take lesser amount of memory. And there are other advantages, not getting into that. This one is easy to understand, right? So everything has their advantages and disadvantages. Register memory based. Now this one is interesting. So ALU can operate on data stored in the register as well as memory location. So if I say add R1 and 2000 M 2000 each, what does it mean? It basically means that add whatever is stored in R1, that is 3, and in some memory location, that is 2000, H is for hex, okay, in some memory location 2000 each, H is hex. I hope you know basics of hexadecimal numbers and stuff. So there will be some data stored, that is 32. So what this instruction means, basically I am telling you to add R1 plus whatever is stored in location 2000 and add that. So 3 plus 32 would be 35. Cool. Then there are complex system architecture, ignore this, and then there is stack based architecture. What does stack based architecture basically means? I will explain. Okay, so basically if I have 2 items in the stack, or it's not like 2 items, if I have more than 2 items in the stack, let's say this was location 0, location 1, location 2, this is 3, this is 2, this is 1. Okay, now if I say, if it's a stack based architecture, if I say add, what it will do, it will simply add these two operands together and then store it in the stack. That will be 5. So now in the stack 5 will be stored. So what does stack do? Stack performs the operation on the last 2 elements that are present in the stack, and of course your stack pointer will be incremented by 1 because your stack pointer always points to the top of the stack. Okay, so yeah, I will explain this with example here. So if I have to perform this operation, x equals to p cross q plus r cross s, and how will I perform this? If I have these kind of architecture, right, stack based architecture, accumulator based architecture, and register based architecture. So there are different ways. How will I perform this operation in stack based architecture? So I want to perform multiplication. So first we will use Bodmer's rule. What does Bodmer's rule tells us? We need to store the multiplication, right, somewhere. For that, first the data needs to be in the stack. So first what I will do, I will push P, I will push Q. So now in the stack, P and Q are stored. Okay. Next what will do? Next I will write mul. What does mul means? Multiplication. If I just write mul, right, the computer will understand because it is a stack based architecture. I'm just telling the computer to perform the multiplication of the last 2 elements of the stack, basically the top of the stack, that is P cross Q. So it will perform the P cross Q and again it will store it in the top of the stack. So P cross Q will be stored in the top of the stack. Correct? Okay. Now, before this, right, what we do is we also, before storing this, okay, sorry, the result, sorry, it is not stored in the top of the stack, sorry. this I was wrong. It is actually not stored in the top of the stack. Sorry, I had explained here wrong. It is not if I do addition, if I do add here, what happens? It will add the elements in the top of the stack 3 plus 2, and it will store in the accumulator. I'm sorry, it will not store in the top of the stack. It will not store in the top of the stack. It will store in the accumulator. Okay, mistake. It will not store in the top of the stack. The result will be stored in the accumulator always. So if I'm performing multiplication, the result will be stored in the accumulator. Got it? Now what I will do, I will perform pop and again pop. If I do pop, all this data will be deleted. Next, what I will do, then I will do push accumulator. So whatever was the data stored in accumulator, that is the result P cross Q, that will be stored in the stack now. Next, what I will do, next I will push R, I will push S, and same thing will happen, right? Again I will perform the multiplication, then again I will pop, and then again I will get the value in the stack, that is R cross S. Now next what I will do, I will do add operation. So add operation will perform what? The addition of these two particular elements. So ultimately that will be stored in the accumulator, right? Then I can push that to the stack, or whatever you want to store, you can store that. Okay, so that is what happens in a stack based architecture. So these are the instructions, although everything is not same here, right? So here I had written extra instruction for pop and pop to not store the values, these values. If you want, you can store these values, that's up to you. But ultimately you will have to pop, because at later stage you want to add these two elements, right? So these are all the instructions that you will need to perform. So how many instructions are there? Actually, what happens? So push accumulator, right? So there is total 1 2 3 4 5 6 instruction, and then again similar 6 instruction will be there to get to R cross S, right? And then again there will be add instructions, that is a 1 instructions, and then again you will have push the accumulator or store anywhere, right? So overall this is 6 instructions, again another 6 for R cross S, and again 2 for storing the addition, for adding and storing it, right? So 6 plus 6, that is 12, plus 14. So total you will need 14 instructions. Ignore this, okay, because like this was performed on an older architecture, so that's why it is wrong there. Overall, like now I'm telling you you need 14 architecture, but sorry, you need 14 instructions, but it all depends on the type of the architecture, right? So here I'm talking in general terms, but everything will be explained, how does the stack work and stuff. Okay, otherwise if it is not explained, then you will solve it like this by default. Okay, so number of instructions is 14. So so each of these instructions are actually called as micro instructions. Micro instructions, so or also called as sometimes micro operations. Micro operations. So you cannot break your instructions further than this. Okay, this is the lowest level that we are talking to. So this is the lowest low level language. This is the language of CPU. After this, what happens? Conversion of zeros and ones. Okay, so how many micro operations? 14 micro operations. Similarly, for a single accumulator based architecture, how many operations will I need? So first we need to load the data into the accumulator, let's say P. Then I will perform mul q. What does it mean? It basically says multiply q with the accumulator, because we are following single accumulator based architecture. So if I write mul q, q is already there. If I do mul q, it knows the other operand is stored in the accumulator. So mul q and the result is stored in the accumulator, that is p cross q. Now if I want to perform r cross s, right, I first of all have to store this p cross q somewhere, otherwise this will be gone, and I need this to perform to get to this result, right, p cross q plus r cross s. So we store it in some intermediate result temporary register, that is t1, or any general purpose register you can store it. So this is another instruction, another micro operation. Next again the same repeat, right, we load this to r. So load the value r into accumulator, then perform mul of s, so s cross r, then store it in again. Either you can store this in a temporary register or you can directly perform this, right. So the result is stored in the accumulator. So now I can directly perform add t1. What does it mean? It basically means perform the addition with the value stored in accumulator. t1 is p cross q and accumulator has r cross s, and then store the result at x. So store the value in accumulator, that is p cross q plus r cross s into register x. So how many total steps? 7. So I only need 7 instructions. So the instruction number of instructions has been reduced. Here I needed 14 instructions. So obviously each instruction, right, it is nothing but a combination of ones and zeros. It also needs to be stored. So the size of the instruction also will be reduced. So that is good. It is similar to your app size. You know, your games, right, PUBG and stuff, they take higher size because they have a lot of instructions. So if you are able to reduce the size, that is beneficial to you. So then we have general register based architecture. It is similar, right? So you will move, there will be general purpose registers r1, r2, r3, and you can store the results there. Move r1 to p. So whatever is the data p stored, that will be moved into the general purpose register r1. So sometimes this is also called as this r1 arrow p. So this kind of notation also may be there in the exam hall. You will have to understand that they're talking about this instruction. So what is this mul r1q? That is r1 cross q. Okay. And then store it where? Store it in r1 only. Okay, not in r1, sorry, in the accumulator. Store it in the accumulator. Okay. So if it is stored in accumulator, it will not work. So because it is a general register based architecture, although everything will be explained to you in the question, if nothing is mentioned, you will assume after performing this operation, right, it will store the values back into that register, the result. So r1 cross q, that is p cross q, will be stored in r1. Similarly, move r to r and then perform multiplication, that is r cross s, that will be stored in r2. Okay. Then again, so r2 has r cross s, r1 has p cross q. Then I will perform r1 r2, that will be p cross q plus r cross s, and ultimately the result will be stored in again r1 because this is add of r1 r2. So in the first register it will be stored. Now you might have a doubt, sir, how do I know in the first register it will be stored? Why not r2 it will be stored? So generally it will be given to you in the question, and it should be given in the question. If I'm doing add r1 r2, what does it mean? It basically means this will be given to you in the question. Don't worry, this will be given to you in the question. That is my expectation. If it is not given to you, then listen to me very carefully and follow this. So perform r1 plus r2 and store the result in r1, the first operand. Although I totally agree, how do I know? Yes, we don't know. This should be given in the question, this particular thing, right, where it will be stored. But if it is not given in the question, then you'll have to go by this method. By default we follow this, but it should be given in the question. Got it? Okay. So here if you see, I only need 6 instructions. So the number of instructions reduces. So depending on your use case, you will use that particular architecture. Okay, every architecture has their advantages and disadvantages. So again, multiple things are there for accumulator based architecture, register based architecture. You can pause the video, have a read. What does each architecture does? I will not be able to explain every single thing here. That's why notes are there for you to read. I have explained most of the things, whatever is required. So yeah, let's begin with this question that came in GATE 2021 from EC branch. Okay, so whatever I'm teaching, it has been asked. So mainly three questions have been asked till now, and there is a question of 2024 as well. That of course we will solve later. Okay, like for that we will need bit more knowledge. After that we will solve it. So let's first solve this question. So this is based on stack architecture. Okay, so here what are they doing? They're telling me that the content of the registers R1, R2, R3 are this. So there are few registers whose contents are this. The following machine instructions are executed. Push R1. What does it mean? So I have always told you the stack pointer will always store the top of the stack. What does it mean? So there was previously a temporary data in the stack. Okay, there will be some temporary data, right? It can be anything, garbage value, anything. The stack pointer will point towards this, right? Let's say this value is anything. Let's say 100, anything. Okay. What will happen? If I say push R1, what does it mean? Push the whatever the value that is stored inside R1 into the top of the stack. So I want to push to the stack, right? So what will happen? I want to push R1 has what? R1 is 25H. Now I hope you know what is H, right? It is hexadecimal number. If you don't know, look it up. Okay, you are engineer, you should know what is a hexadecimal number. So push R1, that is 25H. That basically means that push this value into the top of the stack. So first what I will do? First I will increment my stack counter to 1. Sorry, stack pointer to 1. So SP will now become SP plus 1. That is 101. And then I will push this value into the stack. 25H. Next instruction, push R2. So again same thing, I will increment my stack pointer by 1 and then I will push R2. R2 is 30H. Next, I will increment my stack pointer again because I am doing push R3. This will be 40H. And my stack pointer is currently pointing towards 103. Cool. Now what I am doing pop R1. What does it mean? Pop whatever value that my stack pointer is pointing to R1. So what is my stack pointer pointing? It is pointing towards 103. What is the value? 40. So 40 will be stored in register R1. So this is gone out of the stack. Next, so my again what happens? As soon as I do the pop operation, then the stack pointer reduces its count. It will be now stack pointer will point towards 102. Next we have pop R2. That basically means pop whatever contents are present in the location of stack pointer 102 because my stack pointer is pointing towards 102, that is 30. So your R2 will be 30H. Next, what is the next task? Pop R3. So because this already has been popped out of the stack, this is gone. My stack pointer again has reduced to 101. My stack pointer again is pointing to 101. If I say pop R3, so whatever is my stack pointer pointing towards, that will be equals to my R3. So again this 25 also will be popped out of the stack. So whatever was popped in, everything is gone. So again I am back here. So my stack pointer is currently pointing towards to its previous state. What are they asking? They are asking me that after execution the contents of register R1, R2 and R3. So R1 is 40, R2 is 30, R3 is 25. So R1 40, R2 is 30, R3 is 25. So option A is correct. So they are expecting you to know the stack pointer mechanism. They're respecting how the stack memory works. So yes, these things are important. These things are important. You cannot just ignore them. So very important question. You should again revise it. Yeah. So now we will move on to other topics. So this one is the next topic that we will learn about, that is micro operations. What are micro operations? So micro operations are nothing but the low level operations performed on the data stored in the registers within the CPU. So basically, right, when you say add R1, R2, what is that? What does it really mean? It's very simple, right? Whatever are the contents that are stored in R1, whatever are the contents that are stored in R2 register, add them and store it in accumulator. If the architecture is accumulator based architecture, correct? So for you it's very simple. But again, I have told you, right? Computer is very dumb. So you will have to break each and everything down into simple steps. Just like this, right? Here, when I was explaining you this question, if I just would have written it directly that R1, R2 and R3 after the end of operation will be this value, will you understand? No. After everything, after explaining everything step by step, first we push the data, then we pop the data, and that's how the R1 value got exchanged, right? Then you got to know that yes, that is what is happening. That is why the values are getting interchanged, right? So I had to explain you step by step. Similarly here also, if you directly say add R1, R2, computer does not understand. You will have to break it down into smaller steps. So it is similar to an atom, right? So atom is the smallest particle. Inside that we have electron and protons. Can you go anything lower? I mean anything smaller than electrons or protons? Till now, no, right? Till now, no. But there are some quantum mechanics, so that is still on the development stage. Still now, till this date, we don't know any smaller object than electrons or protons, right? They are the most smallest object that can be defined. Correct. So say here as well. So micro operations are nothing but the small actions that the computer will perform. Who does it? You don't have to worry about it. There is a compiler that does all this. So I will explain few basic examples of micro operations. You will understand it even better. Like register transfer. If I say I want to move whatever is stored in R2 to R1. So R1 again is a general purpose register. So this, right, R2 going to R1, what does it mean? It basically means copy the content of register R2 content, right, on R1. Remember, R2 and R1 are just registers, they are locations, right? Just like your house is a location, but the actual content is inside the house. I'm sorry, I meant your address, right? Address of your house is just a location. So this R1 is just a placeholder. Like in front of your door, you'll have a name card, right? Like Mr. and Mrs. something. Okay, if you're married. If you're not married, then obviously your father's name will be there, something like that. So similarly here as well, R2 and R1 are just placeholders. So if I assume a 8-bit system, right, 1 byte system, that basically means each registers will have 8 bits. So this will be my register R1, this will be my register R2, and there will be 8 bits. So there will be 8 cells, 1, 2, 3, 4, 5, 6 and 7 and 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Sorry, 8 is there. Here also 8 bits. 1, 2, 3, 4, 5, 6, 7 and 8. Right, so 1, 2, 3, 4, 5, 6, 7, 8. Correct. Now, what you're doing? You are basically what I'm saying here, copy the contents of R2. So R2 may contain a 8-bit number, right? So it will be any 8-bit number. It can be like 10, 10, 10, 11, any 8-bit number, right? So whatever was previously present in R1, that will be overwritten by this number. So now R1 also will have the same 8-bit number because we are moving the data. So 1010 1011, and this particular thing is called as a micro operation because you cannot break it down even further, right? How do you break it down? You can say, okay, copy the first bit, then the second bit. No, Like micro operations is for our understanding basically, although the computer also obviously will break it down even further, but this much is enough regarding micro operations. uh, why is it important? I will come to this. We'll do some questions, you will understand why are these important. Okay, so yeah, then we have arithmetic operations like perform task like additions and subtraction. So if I say r1 plus r2, so this is a micro operation, right? Addition, r1 plus r2 is a micro operation. Then again moving it back to the like whatever was the result, not storing it in the accumulator but storing it in register. So again another micro operation. So there are total 2 micro operations. Again this is, although this is almost similar but not exactly, this is called as memory transfer. You might have a doubt that sir, this and this are the same, right? No. So I have told you, so these registers are stored where? Pause the video, tell me. These registers are stored where? So whenever I say R1, R2, all these things, right? These are all my general purpose registers. General purpose registers. Hold on a second. GPRs. These are stored where? I've told you, right? These are stored in the CPU. So these are very fast. Now it might happen the data that my CPU wants is not stored in the general purpose register. It is stored in the main memory. And main memory again, it is like this. So there is some address and data. So let's say this is the address 100, this would be the address 99, this would be the address 98, like this, right? And it will go on. This is in hex. Cool. So here what is the problem? The problem here is yeah, actually this will not be 99, right? Because yeah, if I'm saying hex, because hex follows a different different notation. Let's not get into that right now. Let's just stick to decimal. Let's just stick to decimal, right? So decimal, this will be 100, decimal, this will be 99, this will be 98, this will be 97, like this. Now, and let's say I have this general purpose register, 8-bit general purpose register. So this general purpose register actually does not have the data. It does not have the data. This general purpose register has the address, the location of the data. So let's say if the data of my concern is stored in location 100 of main memory, this is my main memory, then what will I do? I will simply, so, and that this location is stored here, right? Information regarding the location is stored in the general purpose register R1. So if I say memory and then I say go into any, so memory and this register, right? Here we are using address register where basically address is generally stored, but also you can use any other register. So this is called as indirect addressing, that will be taught to you in the next chapter. I'm just giving you an overview here, that if I say memory R1, what does it mean? Don't worry if you don't understand this right now, don't worry. Okay, I will again teach you this later on as well. Memory R1 basically means whatever is the data stored in the R1, right? That is, the CPU understand that is a memory location. So here if 100 is stored in this 8-bit data, 100 decimal is stored. So I will go into this location 100 and I will do whatever the instruction tells me to do. So in this case, what is the instruction telling me to do? So copy. So just ignore this for now. Let's take this example. Okay, R2 is getting stored with memory of R1. So if R1 has 100 stored, so it's not like the 100 value will be stored in R2. No, I will go into the location, because this 100, the CPU understands this is a location, and I will go into this location, and then whatever the data is, that I will store in register R2. Now you might have a doubt, sir, how do I know that if M is written, then I have to do this? Don't worry, you don't have to know it. Most probably you will get an idea in the question. Okay, they will give you some hint in the question so that you will realize whether you were using this kind of indirect addressing, right? This is called as indirect addressing, or we are using normal addressing where I am directly taking the contents of registers or whatever. Don't worry, you will understand it. Okay, so in this case, what is happening? This example actually, what is written here? Here we don't load the location that is stored in R1, we actually load the location that is stored in address register. You remember, right? I have told you that the address register will contain the addresses of the data or sometimes the instructions, right? So it is taking the location from the address register. This is also a valid point. So it takes the location and then whatever location that this address register points to, it copies the data. That's it. Okay, that is what we do. Don't worry about anything. Then we have control operations like incrementing and decrementing the program counter, right? So whenever one instruction is completed or it is executed, I have told you, right, what happens? The PC value, the program counter value increments by 1 because it wants to preload the next instruction, right? Whenever the CPU asks where is my next instruction, it wants to preload that. So CPU gets the next instruction because the program counter value has been increased. So this is also called as a micro operation. These are a few examples. So let's solve few questions. With this we will understand even better what is actually happening with the micro operations. So for the following micro operations, so what will happen? So micro operations actually are for you to understand. Okay. Although I have told you computers also follow something similar. Yes, computers also follow something similar. They also follow the operation of micro. They also follow the concept of micro operations, but there what happens? It's even smaller. Okay, for computers, because we reduce it down to ones and zeros and we break it down into more steps. I will explain few of them later on in this lecture only, but the computer might break it down into further steps. So this is for our understanding. Okay, so yeah, pause the video and try this out by yourself. So they are telling me that for the following micro operations, what will be the final content of register R4 if the content of the memory address 2000 is 3. So memory address, I have a memory address that is 2000 that has a content of 3, and register R4, they are asking what will be the value of the register R4. Okay, now like in gate, right, everything will be mentioned to you properly, that what does this M basically means, or you will realize it. M, like you can see the nomenclature here and you can understand this basically means whatever is the content in memory location 2000, store it in R3, right? Okay, you understand this because I have explained you this just before this, and in the gate examination they will tell you, they will explain you what does this mnemonic means. Like most probably they will. If they don't, that's what can I say, then you'll have to understand in the lecture itself, right here itself, that okay, this basically means mem copy. So yeah, now okay, this is the current scenario, right? Let's check the option A. In the option A, first we are performing this micro operation where I say whatever is the content. So this M2000 basically means go into the memory location 2000 and check the content and copy it to register R3. So R3 will now contain 3. Correct. Next, what will happen? Next, I see copy the content of R3 to R4. So R4 also will contain now 4. Next, what is happening? Next, I am performing R4 plus R3 and storing it in R3. So R3, sorry, R4. So R4 will be equals to R4 plus R3, right? So basically 3 plus 7, that is the result. 7 is the result. 3 plus 4, 7 is the result. And that will be stored in R4. So R4 will contain 7. Okay. So yeah, I actually had already drawn it, but never mind. Okay. So R4 will contain 7. So that will be your final, hold on a second, R3, R4, sorry, what am I doing? So I'm copying the contents of R3 into R4, right? So R3 currently has what value? 4. So R4 also will contain 3 only. Why am I writing 4? So R3 plus R4 will be what? 6, not 7. Sorry. So this will be 4 only, right? So it will be 6. Cool. So R4 will contain 6. Let's read the second option. I mean, second case. So here we are storing the value that is stored in memory location 2000 to R3. Okay. So whatever is stored in location 2000, we are storing it in R3. So the same scenario. So your R3 is equals to 2. Next, if I reduce the R3 by 2, if I reduce the R3 by 2 and then store it in the memory location 2000, what has R3? What is the value of R3? It is, sorry, it is 3, right? What am I doing? R3 value is 3, right? Sorry, what am I doing? R3 value is 3. Okay, because this memory location is 3 only, correct? So then what I'm doing, I'm reducing my R3 value by 2 and then storing it in the memory location. So now the memory is getting updated, and that is totally valid. You can do it. So what is R3 minus 2? That is 1. So 1, just hold on a second. Okay, my network is off. So 1 will be stored in the memory location 2000. So the previous value 3 will be overwritten. It will be now 1. Next, what is happening? Next, they are telling me that add the value of R3 with the memory location stored in, with the value stored in location 2000 and store it in R4, right? So R4 value will be what? R4 value will be simply R3, that is 3, plus memory value stored in location 2000, that is 1. So it will be 4. So now the R4 value is 4. It is not 1 anymore. It is not 6 anymore. Okay. So yeah, these kind of questions can be asked. Very simple, right? It is just telling you some a plus b arithmetic. But most people will not be able to solve it because they don't understand the mnemonic. So you have to understand the naming and code, basically the language. Got it? Now here, right, just understand this thing. Here all the values are in decimal. Okay, it may happen they can give hex numbers. If they give hex numbers, then you will solve according to hex. Cool. Yeah. So as I told you previously, though, so if you know a digital computer, it obviously understands only ones and zeros. It works on digital logic. So but we don't understand this, right? We don't understand this. So obviously we write the codes in high level language. You already know this, C++, Python, and then what happens? You have a compiler and interpreter, and the combination of them converts them into low level language. Okay, not getting into that, but it is bit important to understand the instruction set architecture. So this instruction set architecture, instruction cycle, all this is for us to understand. Okay, the machine readable commands are basically generated by the compiler, which converts this, right? So all this fetch, all this, right, micro operations, these are for our understanding. So the compiler actually breaks it down even further. Okay, that is the only thing that you have to understand from these things. Okay, you can read about high level language, all these things, but not super important, so I'm skipping all this. Yeah, this part is important. This part is important, the opcode generation part. I've already told you that the CPU needs to understand what instruction it needs to perform, right? Like addition, multiplication, subtraction, division, anything, correct? Now, and move operation also, right? So for every particular operation, there has to be a opcode, there has to be a mapping. So let's say if I want to perform addition, because the computer only understands add a plus b, because the computer only understands ones and zeros, so maybe if I design a architecture which has only 4 operations: add, subtract, division, or let's say move and multiplication, and your computer only understands ones and zeros. So can you tell me, can you pause the video and tell me how can I explain these 4 operations to computer? How can I explain these 4 operations to my computer with the help of ones and zeros? So how many bits do I need to explain to my computer? So what you can do some mapping. So like, although you can see the picture here, you can understand. So what we can do, we can map addition operation to opcode 0 0. We can map subtraction operation to opcode 0 1. We can map move operation to subcode 1 0. We can map multiplication operation to opcode 1 1. So what does computer understand? If I write add a plus b, so internally the compiler will convert this add into 3. The compiler will say to the computer 3, and then this a also will be a number and this b also will be a number. So then the CPU understands, okay, the control unit, sorry, your manager, right? Your manager understands if they're talking about 3, that means it is addition operation. So your control units will send addition control signals. Your control unit will send addition control signals to the ALU, and your ALU, after receiving the addition control signals, it will add the two numbers. Okay. So if I have only 4 operations, I will need the opcode length, right? The length of the opcode. This is called as the opcode length. This is called as opcode. It will be 2 bits because I have 4 states. So how many bits I need to define 4 states? 2 bits. And this will change depending on the number of instructions or operations you want in your architecture. So if someone says it's a 32-bit processor, although this is not exact definition of it, but you can get a bit idea. You can get a bit more idea what is the difference between 32-bit processor and 64-bit processor. Okay, I'll just give you a bit of idea, not the exact definition. Again, I'm just giving you a bit of intuition. So 32-bit processor, you can roughly understand that it can have up to 3 raised to power 32 different operations, different outputs. This many amount. Here, how many bits I had? 2 bits, right? 3 raised to power 32 is a very large number. And 64-bit processor will have 2 raised to power 64 processor, 2 raised to power 64 different operations that the CPU can perform. So which one will you prefer? Of course, you will say, sir, I will prefer this. You are correct. And most of our processes now run on 64-bit only. But what happens is they are more resource hungry as well, because this will take more storage, more bits to store. So there are certain disadvantages and advantages. Let's not get into that right now. Just I hope you understand the difference between these two, right? And if you did, hit the like button, because I know everyone uses computer, but they don't understand what is the difference between 32-bit processor and 64-bit processor. Okay. So yeah, so every instruction, right, can be divided into a operation code like add, subtract, move, and an operand. Operand is the one in which I will perform the operation, and operation code is the operation that needs to be performed. Okay, I've already explained all these things. So yeah, so there will be an instruction set architecture to a computer. What do I mean by instruction set architecture? So if we want to perform data transfer, it will support move, LDA, load. So these are all called as different kinds of instructions. So this LDA basically means load data to accumulator. Okay, so if I write here, if I write that move R1 R2, so that basically means whatever is the value in R2, store it in R1. Now you might say, sir, how will I know this? Generally they will explain you what each operation means in the question itself. If they are not explaining you, that means it is very simple. Take the default case. So if nothing is mentioned, and if they are telling you move R1 R2, then how will you interpret this instruction? That you will interpret it like this: move the value of move the contents of R2, whatever is stored in R2. So currently, let's say R2 has a value 3. So whatever is stored in R2, move it to R1. So R1 also will have the value right now 3 stored. Got it? So yeah, that is what happens. Similarly, for arithmetic and logic, we'll have these kind of instructions. For machine control, I will just give you a bit of overview, like what does this each instruction means. You already know what does this mean, right? What all this means, and or operation you know, but you might not know this: halt, push, pop. So push, you know, push the value into the stack, pop from stack. Halt basically means what? Halt basically means I have performed a certain set of codes, execution of instruction, right? Then halt basically tells the CPU to stop its execution, don't perform anything. Okay, so it basically takes the CPU into a not working state. Okay, it just remains at rest. That is what halt means. HLT basically means halt. Iterative basically means loop. So if you see, if I say, I think you must have written a C++ code that if I say int I equal to 0, then I plus plus and I say I less than 100, right? So basically what does it mean? So here I will have certain set of code that it will execute, and actually this I plus plus is on the right hand side. Now it will perform this code 100 times, right? So that is what loop means. Here also same thing. If I say I4, if I am performing 4 instructions, right? So it will go sequential. So your program counter will always be incremented by 1. But in this case, what will happen? After performing I4, in the instruction itself, I say to change the program counter value to 1000. Okay, and perform this loop 100 times. So it will perform these 4 instructions 100 times. It will perform I1, I2, I3, I4 100 times. Then we have branching. So branching is, as the name suggests, we will branch out to some other instruction, right? So after I4, our PC value should go into 1004 technically, if there is no loop. But we will not go to 1004. In I4, I will change the PC value to some other, PC basically means program counter, right? PC value to some other location. So the next instruction will not be fetched from 1004. Next instruction will be fetched from 2000. Because in the instruction itself, I4 itself, I am changing the program counter value. Okay. So just giving you a few examples, not explaining everything because not super important. But you will get the idea as you do more questions. So then I will just explain you bit of difference between bit, byte and word. So bit, as you know, it's the smallest unit that the computer can understand. It represents two states, 0 and 1. What is a byte? Byte is a combination of 8 bits. Okay, standard unit for storing data, representing single characters and stuff. Now, what is a word? This is interesting. What is a word? Word is the number of bits the CPU processes as a single unit. Right? If you see 16-bit, 32-bit, 64-bit. So it is similar to the, so this is a definition, whatever I explained here, and this is also another definition, the number of bits that the CPU processes in a single time. Okay, higher the better, it is able to process more number of bits. Okay, that is also another definition of the bit basically. So this is one of the definitions, that how many opcodes it supports, and this is also another definition depending on the architecture. Okay, depending on the architecture. So let's do a basic question. On the size of memory and gate, I am expecting they will ask a question next from this. Okay, this is a very good topic and very scoring topic as well, and I'm expecting they will ask a question from this. You already know what is address lines, data line you don't know, but after solving this you will be able to solve this. You will be able to understand what do I mean by data line. Okay, read the question, try it out by yourself, then I will solve. So here they are telling you the capacity of a memory unit is defined by number of words multiplied by the number of bits per word. The capacity of a memory unit is defined by the number of words into number of bits per word. Okay, so basically it's in bits only, right? How many separate address lines and data lines are needed for a memory of 4K 16? 4K into 16. So 4K means what? 4K basically means you have 4K words in the memory. You have 4K words into 16, and the bits in each word is 16. Okay, so what is the capacity of your memory? For 2 raised to power 2. So capacity of memory is defined by this. So can you tell me, I have just told you that what does a word mean? Word basically means how much the CPU can process at a single time, correct? So in this case, the CPU can process 16 bits at a time because number of bits per word is 16. Now you know your CPU can process 16 bits at a time. So all these memory cells, right, will be of length what? 2 bytes or 16 bits. So each cell length will be 16 bits. Because why 16 bits? Because your memory, because your CPU processes the data in the form of words. Like you, right? You understand English in the form of words. I will say a word, I will say a sentence, you will break it down into words and you will understand what does it mean, what does each word mean, and you will compile that. Your brain compiles that. So same thing is happening over here. The CPU understands in the form of words. So again I am telling you, in the question, although here it is not mentioned, but it will be mentioned whether your CPU is word addressable or byte addressable. What does word addressable means and byte addressable means? It is very simple. Like word addressable basically means your memory or data will be stored in the form of words. So each cell will consist what? A word. Okay. There are many versions of this, advanced version as well. But for now, for your purpose, you don't need to understand all this. All you need to understand is word addressable or byte addressable. So word basically means each cell will contain a word. So 16 bits. If it is byte addressable, as the name suggests, each particular location will contain 8 bits of data. It is byte addressable. So each particular cell will have 1 byte of data. Okay, 1 byte of data. So, yep. Now let's come back to our question. Okay, so each particular cell will consist 16 bits, and 16 bits, how many 16-bit cells I have? 4k. 4k means what? 2 raised to power 2 into 2 raised to power 10. That is equals to 2 raised to power 12. So 2 raised to power 12, 16-bit cells I have. Correct. So the CPU will take the data from here. So how will the CPU take the data actually? So first there will be a mux that will select my location, right? So how many select lines do I need? How many different addresses do I have? 2 raised to power 12. So how many select lines I will need? 12. I will need 12 select lines. So how many address lines I will need? 12. So it can be either option C or option D. Of course it will be option C only, because there needs to be 16 data lines. Why? Because while selecting the address, right, you have to select out of 2 raised to power 12 a single address, right, and that depends on the 12 bits, correct, because each address will have 12 bits and you will select an unique address. But data, right, you need all the data from here, right, and each bit, each information can only be carried through a single line. So if I want the CPU to get all the 16 bits of data, how many data lines do I need? 16, because each line will have a single bit of information. For address, what was the length of the address? If I had 4 addresses, 1 2 3 4, what was the bit length? 0 0 0 1 1 0 1 1. So what is the bit length? 2 bits. So I need 2 bits of information. So how many lines I will need? 2. But in this case, I have 16 bit of information. How many lines do I need? 16. So that's why I will need 16 data lines. Okay. So if your computer is word addressable, then you will define it like this, like I have told you, right? If it is word addressable. Okay. Now, if your computer is byte addressable, I will explain that part as well. Then what will happen? If I would have told you that your computer is byte addressable, right? If it was byte addressable, then this number is not proper. Okay, this number is not properly written. It should have been written like this. If it would be 8k into 8. Okay, although the multiplication value, numerical value, both of them are same, but they mean different things. So here it is proper. It is byte addressable because each particular cell consists of 1 byte. Correct? So now you will say, how many data lines do I need? 8. How many address lines I need? 13. Okay, I will need 13 address lines. So this is the trade-off. So number of data lines reduced drastically, address lines only increased by 1. That is a good thing. But now your CPU is processing less amount of data at a single time. Correct? So yeah, that is also another problem. So there is a trade-off. That is what they do while in the designing phase. Okay. So there is a bit of formula. I don't want to get into the formula right now. So this capacity of memory is basically 2 raised to power m number of address lines into n. But you get the formula, right? You after explaining all this, you will get the formula. So let's solve a question, and let's see if you are able to understand it or not. Correct. So here a processor can support maximum memory of 4 gigabytes. So it can support maximum, the capacity of the memory is 4 gigabytes, right? 4 gigabytes. So in bits or in bytes, what it will be? It will be 4 into giga. Giga basically means what? Giga is 10 raised to power 9. That is equals to 10 cube whole cube. So this will be equals to 10 cube in computers, right, is roughly 2 raised to power 10 whole cube. Okay, so this will be 4. Actually giga, the exact value of giga is this only in computer terms. Okay, so this will be 4 into 2 raised to power 10 raised to power of 3 bytes. Okay, this is the capacity of the memory, where the memory is word addressable and a single word consists of 2 bytes. So memory is word addressable, right? So a single cell is 1 word and single word is equals to 2 bytes. So a single cell will contain 2 bytes of data, that is 16 bits of data. And I will have data like this and this so on, right? The size of the address bus of the processor is at least how many bits? So how many different address locations I have? How do I calculate it? So I know this is the overall capacity of the memory, overall capacity. What is it equals to? It is equals to, I've already derived the formula, I'm just using it. It is simply the total number of memory locations. How many memory locations I have? 2 raised to the power of m, where m is the number of address lines, into the data stored in each location. If this is in bytes, then this value also will be in bytes. If this is in bits, then this value also will be in bits. Got it? Because of course units have to match. So this is unitless. This just tells me how many total unique addresses I have. Here I need to write the data stored in each unique address, and that will give me the overall capacity of the memory. So this will be 2 bytes, because each unique address stores 2 bytes as explained here. It is word addressable. So from here we can solve. So 2 will be cancelled, byte and byte also will be cancelled now, right? Make sure your units are proper. So this will be 2 into 2 raised to power 30, that is 2 raised to power 31. So your 2 raised to power m is equals to 2 raised to power 31. So your how many addresses I need? I need 31 address lines, right, or 31 address bits. This is the least that I need to provide, right? So your answer would be 31 bits. Okay, so yeah, that's it. You can use the, I'm just directly using the formula, but you can understand it conceptually as well, because this formula came from concept only. Okay, So no need to explain here, no need to get into much, but this is the explanation of this question, and I'm expecting a question to be asked from this, because this concept is very simple. It's not super difficult, right? And COA, they will if they are asking a question, my guess would be they will ask very simple thing. They will not ask very difficult, right? Because they also know students are already very pressurized by studying a lot of things. They would not want to study this much, right? So that is the point. So yeah, I've already explained you the formula, no need to explain here. So one more thing, that if somewhere I write 1 kilobytes, so 1 KB, while B is in small. So if B is in small, that basically means they're talking about bits. If B is in capital, then they're talking about bytes, like here, right? So 1 KB, 1 KB is 2 raised to power 10 bytes. That is correct. But this will be equals to, and what is 1 byte equals to? 8 bits. So in terms of bit, it will be 2 raised to power 13 bits. Okay. So there is a huge difference between capital B and small b. So be very, very careful about that. Be very, very careful about that. Right. So yeah, additionally there are terms like double word, quad word. You don't have to worry about it. Double word basically means 2W, quad word means 4W. Don't worry about it. The difference between small b and capital B, I hope you get the point. Small b represents bit and capital B represents byte. That's it. Okay. So as I've told you previously, right, this 8-bit processor, 16-bit processor, there are multiple understanding of this. One of the ways is the length of the instruction. How big is my instruction, right? So 64-bit processor, the length of the instruction or the opcode length will be higher. That means you have more number of instructions that the CPU can understand, that the CPU can perform. So that is obviously always better. Correct. Got it. So if your CPU, if your processor is 64-bit processor, right? But if your architecture is byte addressable, then it will only be able to support 8 bits at a time, which is sometimes not good. So that's why we made this concept called as word addressable. Then if I say that my CPU will be able to support this many amount of words, then it is good. Okay. So that's why this concept came as word addressable. So if your CPU is word addressable, what you need to understand? You need to understand, if your CPU is word addressable, that the data stored in each memory cell will be equals to the bit of the processor. So if it's a 32-bit processor, then the word length will be 32-bit. So each memory location will store 32-bit of data. Basically, it means that your CPU will process 32 bits of data at once. That's it. Okay, and that will be used to compute the capacity of the memory or anything, number of address lines or anything, right? So let's solve a question. We'll understand this even better. Consider a 32-bit hypothetical processor with support for 128 megabyte of memory. So the memory capacity of this processor is 128 megabytes. So what is 128? It is 2 raised to power of 7. It is 2 raised to power of 7 into mega. What is mega? Mega is 2 raised to power 20, right? Mega is 10 raised to power 6. 10 raised to power 6, which is basically 10 raised to power 3 whole square, and 10 cube is 2 raised to power 10 in computer world, right? So this will be 2 raised to power 20. And of course, don't forget the byte. You know the difference between byte and bits. Don't forget it. So this is my capacity of memory. If the system, it is a 32-bit hypothetical processor. Okay, it's a 32-bit processor, right? 32-bit processor. In bytes, how much is it? 4 bytes. 8 bits is 1 byte. If the system is redesigned to be used as word addressable, so how many address lines would be needed in the updated system? So previously it was getting used as a byte addressable system. Then how many address lines you required? So if it was used as a byte addressable, that means your data line would be how much? 8 bits, correct? Or 1 byte. So this will be 2 raised to power 27 into 1 byte, because your data line will always be 1 byte if it's byte addressable. How many address lines you require here? 27 address lines. If it is word addressable, it will process 4 bytes at a time. So I can actually take 2 raised to power 2 here, because each unique location will now have 4 bytes of data. So this will be, I can rewrite this as 2 raised to power 25 into 2 raised to power 2, that is 4 bytes. So this will be my number of data lines. How many data lines do I need? 4 bytes, right? Each bit takes 1 data line. So how many bits is this? It is 32 bits. So the number of data lines is 32. Although this is not asked in the question, but these are the number of data lines. What is the number of address lines? That is what is asked in the question, that is 25. Right? So you will need 25 address lines. That's it. Got it? So previously, how many data lines you required? Only 8, because 1 byte is 8 bits. So 8 data lines, 27 address lines. In the previous case, when it was byte addressable, if it is word addressable, you will need 32 data lines and 25 address lines. Okay? Yeah, so now I want to explain a bit how my CPU processes the data if it's a byte addressable system. Okay, it's a byte addressable, so your memory will be stored in terms of bytes. So this will be 100, 101, 102, all this is in decimal. So it is storing the data in terms of bytes. Here also it is storing the data in terms of bytes, correct? So 16-bit processor versus 32-bit processor, how will the processor process the data? So what will happen? If it's a 16-bit processor, right, so it will take 2 bytes of data at once, correct, because it's 16 bits. So your pointer, right, if it was pointing here initially, it will point here after end of one transaction. Although your memory is byte addressable, but your processor is 16 bits, so the length of the opcode is 16 bits. So of course the CPU expects 16 bits of instruction, but once it comes to 100, this only consists of 1 byte of information. I need 4 bytes, so I need 2 bytes, so it will go and take the value stored in 101 as well, so it will get 2 bytes of data. Next, your program counter will now point to 102. I am talking this about the instructions. Because it's a 16-bit processor, it expects that it needs 16 bits of instruction. It does not get it, so my program counter points at location 100, right? So it needs 16 bits of information, so it will take the next address as well. Okay, it will take these 2 bytes of data, and my program counter will be directly incremented by 2. That is the difference. If it was 32-bit processor, that means each instruction length is 4 bytes, but my memory is byte addressable, then my program counter will be incremented directly to 103. That is the only difference. Program counter will be incremented to 103. That's it. So that is what happens in byte addressable memory. There are a lot of things, but for you, for this one shot, this is the only important thing that you need to understand. In byte addressable memory, the program counter will increment by the word length. What is the word length? 4 bytes. It was 100, now it moved to 103. So what is the difference between 100 and 103? It is 103 minus 100 plus 1. It is 4. Cool? Got it? That is the only thing that you have to keep in mind. So let's solve a bit of questions. A hypothetical processor supports 2 address instruction only. Okay. it supports two address instruction only. What does two address instruction basically means? That means I will have two addresses, right? So I will just give you an overview. First I will have the opcode, which I have already explained. Then I will have the operands. So if they mean by two address instruction, they are basically telling you that the opcodes, the addresses of the opcodes will be given here. So a hypothetical processor only supports this simple kind of instruction, where first I will give the opcode, then I will give the address of the two different operands. If I say add, if you want to add 3 plus 4, right? If you want to add 3 comma 4, how will you add it? So first this 3 will be stored in some memory location, let's say 2000, right? In some memory location it is stored, and this 4, this also is stored in some memory location 3000, right? Memory location 3000, 4 is also stored. So first we will store this value 3 and 4 in the memory location, and then I will write this. I will write add 2000 comma 4000. What does it mean? It basically means this 2000 is the address of the first operand, this 4000 is the address of the second operand, and add is basically the operation opcode. So this also is in binary only. This also will be in binary. Let's say 00. So in my hypothetical processor, 00 basically means addition. Okay, got it? That is the definition of a instruction code, whole instruction code. Okay, so this is the whole instruction length, single instruction. So a single instruction will contain this much amount of data in binary, in ones and zeros. Got it? Cool. Okay, now it's supposed to address, I have told you these are the two addresses. It has 32-bit instruction. I have told you this whole thing is instruction. So they are telling me that my hypothetical processor is 32-bit. That means what is the length of this whole instruction? What is the length? It is 32 bits. Correct? It is 32 bits. Got it? And has 12-bit addresses. So the address lengths each are 12 bits. 12 bits, 12 bits. So can you tell me what is the opcode length? What is the opcode length? Opcode length is nothing but 8, right? Because 12 plus 12 is 24, and out of 32 bits 8 is remaining, so opcode length would be 8. Okay, the length of the opcode would be 8. Got it? So how many different operations can my CPU perform here? 2 raised to power 8. It can perform 2 raised to power 8 operations. Okay, 2 raised to power 8 different operations. Now, but what are they asking? Then the minimum and maximum number of two address instructions that can be formulated. So what is the minimum number of instructions that can be formed? So this particular thing, right, this whole thing is called as a two address instruction. This whole thing is called as two address instruction. Why is it called two address instruction? Because the instruction consists of two addresses. Okay, that's why. Now, how many different two address instructions I can formulate? They are basically telling me that how many different operations I can perform with this format, like addition, division and stuff, right? So each particular opcode will be mapped. If I have 2 raised to power 8 different, so if I have 8-bit opcode, how many different opcodes I can perform? 2 raised to power 8. Why? If I had 2-bit opcode, right, 1 2, how many different operations I can perform? 0 0. will be mapped to one operation, 0 1 will be mapped to one operation, 1 0 will be mapped to one operation, and 1 1 will be mapped to one operation. Correct? So how many total? 4 operations. So how many different instructions? 4. This is equals to 2 raised to power 2. This is nothing but 2 raised to power the opcode length in bits. 2 raised to power the opcode length in bits. Okay, got it? So yeah, that's it basically. So here, what is the maximum number of instructions that can be formulated? This 256, 2 raised to power 8. And what is the minimum? 1. Of course, it has to perform one operation, one instruction, right? Minimum. Okay, so minimum is 1, maximum is 256. Got it? So maximum length, maximum number of instructions will be 2 raised to power length of the opcode. We have derived it. If you want to remember it in terms of formula, you can remember it. Okay. So similarly, there are these are the examples. Okay. So 3 address instructions. You got one example. 3 address instruction. I will have 3 addresses, and the opcode will be the remaining length. Okay. And this 3 address instruction will automatically support 2 address instruction, 1 address instruction. Don't worry, I know you don't understand all this. For now, what you understand is, if you are saying 3 address instruction, there will be opcode and there will be 3 addresses. So there will be 3 operands, and I will give addresses of 3 operands. Now you will say, sir, if I write add A, B and C, where A, B, C are 3 operands, right? Or add 3, 4, 5. You will say, so this is good, right? Because we are able to use more operands now. Previously, this only supported 2 addresses, so I can only do operations with 2 operands at a time. But here I can simultaneously do operations with 3 operands. What is the disadvantage? The disadvantage is it will take up some space, okay, of the opcode length. So the number of operations will be lowered because the opcode length will reduce. So there is a trade-off, and that is why you need to understand architecture, which architecture to choose. Okay, so this is possible, but your opcode length will reduce, the number of instructions will reduce. Now what is the problem here? The problem that you might say, so what if I don't want to do addition with 3 operands? What if I want to perform addition with 2 operands at 3, 4? Then how will I perform it? Then basically what you need to do is, you don't worry about it. Your CPU will automatically support. If your CPU supports 3 address instruction, it will automatically support 2 address instruction. How does it understand? I will explain that. Don't worry. I will explain that. Don't worry at all. But for now, somehow you just assume that if I want to perform operations with 2 operands, your CPU will understand. So if I say add 3, 4 in the same CPU architecture, your CPU understands it, that it's a 2 address instruction, so it will treat it like that. What is the advantage here? Advantage is this: the maximum number of operations increases. So if your opcode is variable in length, right, because it depends on a particular situation, that for now hypothetically you assume that your CPU understands whether it is a 2 address instructions or a 3 address instruction. Okay, if it understands it, then if I write add 3, 4, what will happen? And let's assume a very basic example, like, right, so each address is 2 bits, okay, and your overall instruction length is 16 bits, correct? So if in the same architecture I am using 2 address instruction, so 2 bits is gone here in a single address, another 2 bits is gone in the other address, so overall 4 bits is gone. How many are remaining? 12 bits. So here in the opcode length I have 12 lengths, so I can perform 2 raised to power 12 different operations. But if in the same case it was in the same computer, it was 3 address architecture, then what would have happened? Then basically this was 2 bits, this was 2 bits, this is 2 bits. So overall this is 6 bits. So what is the length of the opcode? 10 bits. So this will be 2 raised to power 10, which has reduced. So the maximum number of operations which I can perform with increased number of addresses has reduced. Okay, but still this is better. Now just one small thing, this 2 raised to power 12 that we calculated, it will not be exactly equal to 2 raised to power 12. Okay, and sorry, this 2 raised to power 10 that we calculated over here will not be exactly equals to 2 raised to power 10. Few of these opcodes, right, few instructions will be reserved out of this 2 raised to power 10. Reserved for what? Reserved for performing this. Reserved for the CPU to understand whether this is a 2 address instruction or a single address instruction. And I'm telling you from the start, Gate is yet to ask a question from this topic. Okay, I'm coming into the addressing, although not exactly into the addressing modes. This is basically the types of instructions. Okay, but if they want, they can. So if we read the syllabus, right? So machine instructions. So it is in the first topic only, machine instructions. Okay, so this is a bit typical topic. So if you are not able to understand it, it's fine. Okay, don't need to take that much of stress, but I will suggest try to understand it, because I am expecting Gate to ask a question from this, and this is a bit of typical concept, right? So the first question that we solved, this is a very easy. Where is it? Yeah. This question that we solved, right? Mostly I expect them to ask a question like this. Okay, but if they want to ask a difficult question, they will ask questions like this, like basically how many 2 address instructions will my system support? Okay, I will come to those questions, don't worry. 0 address instruction. So 0 address instruction basically means I will not have any opcodes. Sorry, I will not have any addresses, right? I will simply have opcodes. So in the opcode itself, the data will be present. Examples, like if I say add, how will add work? If it says 0 address instruction, that basically means, like, there can be many architectures. One of those is this stack based architecture. If I say add, right, that is only the opcode. The CPU will understand if the user is telling me to add, it is talking about the stack. So in the stack there will be 2 values stored, let's say x and y. So it will pop out the 2 values and it will add these 2 values, x plus y, and then it will store it in the top of the stack. Just giving you an hypothetical example how 0 address instruction works. Okay, then we have 1 address instructions, where 1 address is there with the opcode. So you might provide 1 address. So one of the operand it will take from the address, and the other operand it might take from the stack, it might take from the accumulator. And if you have two address of opcode, then it can take the 2 operands addresses, 3 address, like that, right? And I've already told you, if it's a 3 address instruction, it will automatically supports 210 address instruction. If it's a 2 address instruction, it automatically supports 10 address instruction, explained here, right? And why it will not be totally equals to 2 raised to power 10 reserved, I will explain. We'll do a example, we'll understand that, don't worry. Okay, for now let us solve a basic question, very basic question. A hypothetical processor supports 32 1 address instructions only. So it supports 32 1 address instructions. Okay, so there are 32 different 1 address instructions. Okay, that means what? That means this is your number of different opcodes. So from this information you can directly say what is the length of your opcode. That is equals to what? So this is 2 raised to power 5. So your length of your opcode would be 5 bits, because with 5 bits I can make 32 different instructions. If address length is 3 bits, then length of the instruction in bits will be, so address length, this is 3 bits, and this is 5 bits. So what is the length of the instruction? 8 bits. Okay, so this is the minimum length of instruction to support this architecture. Support 32-bit architecture, right? So 32 different opcodes. You can have more, right? But at least you need 8 bits. Yeah. So basically, right? There are two kinds of instructions length. Two types of instruction length variations. Either it can be fixed. So basically, your instruction length, which consists of the opcode, which consists of the address, that will be fixed, or it can be variable. Not in our syllabus, so ignore this. Variable length instruction, basically the overall length of the instruction being variable, ignore it. Okay, that will not be asked. So in your syllabus, we have fixed length instruction, and in fixed length instruction, it can be the 16 bit, 32 bit, 64 bit, and so on. But your instruction length is fixed, but your opcode can be variable. Your opcode can be variable. Why? To support this feature, that even if it's a 3 address instruction, this can still support 2 address instruction. And I told you, out of this 2 raised to power 10, few cases will be reserved. Here also few cases will be reserved. Now we will understand how it works. So let's take a very basic example, that my address length is 2 bits. Okay, let's see, this is my instruction length, 6 bits. So what is the maximum number of addresses it can support? 2 address instruction, right? Because of course 2 address would be 4 bits, and you will have to give some bits to the opcode length, right? You cannot use 3 address instruction, otherwise no bits will be left for opcode. So you have 2 address instruction. So you will always start. So how many unique number of 2 address instruction and 1 address instruction I can have in this particular architecture, hypothetical architecture? Always start with the highest number of address instruction. In this case, 2 address instruction. So if it's a 2 address instruction, and if each address is 2 bits, so what is the opcode length? 2 bits. Opcode length is 2 bits. How many different opcodes I can have? 2 raised to power 2. How many different operations? That is 4. So total I can have 4 different instructions. Now out of this 4, you will chalk 1 out. You will chalk 1 out. Why? So I will explain. So what are the 4 combinations? 0 0, 0 1, 1 0, 1 1. Let's say these 3 represent addition, moving, and subtraction. This you will not be able to, if you are using this as a normal operation as well, you will not be able to support 1 address instruction. Why? I will explain. So let's for now reserve this instruction to let the CPU know if the opcode, if the first 2 bits of the opcode is 1, 1, 1, 1, that means it is a 1 address instruction. So that is how we let the CPU know it is an 1 address instruction. So if this is 1, 1, this will be a 1 address instruction, right? So if I fix this to 1, 1, if it's a 1 address instruction, right, then how many bits are left? 4 bits. It is a 1 address instruction, so only I will use the last 2 bits. These 2 bits will be left. So this part will be the address 1 address part, right? And this will be still left. Correct? So this is the length of the opcode of the 2 address instruction. Okay, so here the overall opcode length is actually 4 bits, but the problem is these 2 bits are fixed. This will has to be 1 1, otherwise the CPU will not be able to understand whether this is an 1 address instruction or 2 address instruction. So CPU checks the first 2 bits. So first 2 bits are gone, reserved. So how many bits are there for you to play? Although the opcode length is 4, but you have only 2 bits left to play with. So this will be 2 raised to power 2, that is 4. So how many different 1 address instruction does this architecture support? 4. Okay. Got it? So this is what we will support actually. Sorry, this is what we will do. Okay, so let me solve few questions. Let me solve few questions. So this is the same example only. Let us solve this. So in this case, what was the unused opcode? How many opcodes were unused in this case? Can you tell me how many different opcodes were unused for two address instruction? For two address instruction, how many unused cases were there? One unused case, because I was using 0001 102 to perform any logical task, but 11 was unused. It was not used to perform any logical task. It was just used to perform this. Explain the CPU that it is an one address instruction. Similarly, if I say here, how many unused states were there in the one address instruction? So although the overall opcode length is what, 4. So actually you should be able to provide 2 raised to power 4 different operations. But actually how many I'm providing? Only 4. That is 2 raised to power 2 minus 2 raised to power 4. So how many unused one address instructions are there? It is 2 raised to power 4 minus 2 raised to power 2. That is 16 minus 4. That is 12. So there are total 12 unused states here, right? I will not be able to use those states. Okay. So yeah, hold on a second. Let me. Where is that question gone? This question will be here. This question will come actually first. Yeah, this is the same example actually. Oh, 2-bit addresses, 2 address. Yeah, this is the solution of this question only. Whatever I have explained, this is the same question. Okay, already explained, so I will not explain it over here again. So how many 2 address instructions are supported? What is the answer? 3. How many 2 address instructions are supported? 3. Right, because 1 will be used to support one address instruction. So if they are asking you the maximum number of 2 address instruction, it will be 4 actually. Then you will say that it will not. If they are asking you what is the maximum number of 2 address instruction, specifically they are saying 2 address, they are not talking about 1 address, then you will say 4. Then you will say 4. Why? Because then we will not have to reserve this particular opcode. Correct? Okay. Now if they are asking you if maximum number of 2 address instruction, how many it can support? 4, right? Because you don't have to include 1 address, you don't have to reserve this particular opcode. If they are asking you what is the maximum number of okay, if they're asking you that unused 2 address instruction, if one address instruction is used, one address instruction is used, then what will be the unused 2 address instruction? 1. One particular opcode will be reserved, right? So out of 4, 1 will be unused. Now if we do a interesting change, if I say that let me not reserve 2 bits, right? What I was doing, I was reserving 1 for one address instruction. Let me do an interesting thing. What is the interesting thing? I will reserve 2 different opcodes for one address instruction. I will reserve 2 different opcodes for one address instruction. What are those? So let's say I reserve 10 and 11 for one address instruction. So total, how many 2 address instruction will I support now? Previously I was supporting 3. Now I will support 2. Okay. So there are 2 total unused opcodes, 2 unused, and these 2 will be used in one address instruction. So in this case, when I support 2 different opcodes for one address instruction, right? Either it can be 10 or 11. So whenever the opcode, the first 2 bits of the opcode is 10, CPU will understand it is a one address instruction. Whenever the first two bits is 1 1, CPU will understand it is one address instruction. So if I'm reserving two states for one address instruction, that will actually increase the number of one address instruction. Here, how many one address instruction I was supporting? I was supporting 4, right? 2 raised to power 2. But here things will change. If you see, now it's a 6-bit instruction. So 2 bits are here, 2 bits are here, 2 bits are gone for address. So I have 2 bits left. So how many different combinations? 2 raised to power 2. Again, I have 2 bits left in this particular case. And both of these are one address instruction. So how many different combination? 2 raised to power 2. So total how many combination? 2 raised to power 2 into 2. So if I have two unused states, let me write it properly. Unused states, then I can have how many different opcodes for one address instruction? 8. Similarly, if you have 3 unused state, you include 0 1 as well. So now how many different combinations you will have? This will be 2 raised to power 2 into 3. Are you getting my point? So what is happening? So you are increasing the number of instructions in one address operation, right? But you are reducing the number of instruction in two address instruction. Okay, number of opcodes, basically number of different opcodes. So you will have a trade-off to make. So all these things you will have to understand. Got it? So there is a summary table. Okay, let me put the summary table here. Where is this? Yeah, this is the summary table. So if I have 3 2 address instruction, how many unused opcodes I have? For the 2 address instruction, 1. So how many different 1 address instructions I will have? 1 into 2 raised to power 2. Similarly, if I have 2 unused opcodes in the 2 address instruction, I will have 2 into 2 raised to power 2. So how many total instructions this particular architecture can support? 7. How many total instructions this particular architecture can support? This is 2 plus 8, that is 10. If I have only one 2 address instruction, right, and 3 of them are unassigned, then how many 1 address instruction I will support? 3 into 2 raised to power 2, that is 1 plus 12, that is 13. If I have no 2 address instruction, then it becomes the case of 1 address instruction only. In 1 address instruction, I have all the 4 bits as the opcode length and 2 bits as the address length. So how many different opcodes I can have? What is the total number of bits here, right? So this is 2 bits of address and this overall was 6 bits. So this will be 4. So this will be technically 2 raised to power 4. And let us see whether we are getting it from our formulae or not. So this will be 4, that is number of unused opcodes in the 2 address instruction into the opcode length of a 2 address instruction, right? That length. So that is 2 raised to power 2. So this comes out to be what? This comes out to be 2 raised to power 4 only. Correct? So this will be 16 only. Okay. So yeah, I hope you get the point. You understood the thing. So this is the formula. So if I have no unused opcodes, right? Out of 4, all 4 I am using for 2 address instruction, then how many 1 address instruction I will have? 0 into 2 raised to power 2, that is 0 only. So total I will have 4 instructions. Okay, and this particular thing, these two are called as fixed opcode length. Here your opcode length is not varying. What is the length of opcode here? 4 bits. What is the length of opcode here? 2 bits. And these all are called as variable opcode length. So I hope now you have understood this part, and I'm expecting if they are framing a very good question in GATE, they will frame in from this topic. Okay, so yeah, let's solve a good question from this, right? From this topic. This is the question. A hypothetical processor supports 2 address instructions. and one address instruction. Okay, so it supports two address instruction and one address instruction. It has 32-bit instruction and 12-bit addresses. If there are 254 two address instruction, so there are total 254 two address instructions. So what is the opcode length? Each address length is 12 and this is 32 bits, so this will be 8 bits, correct? So how many different two address instruction can my processor support maximum? This will be 2 raised to power 8, that is equals to 256. But out of this 256 we are only using 254. So how many states are unused? 2 states are unused. Okay, then what they are asking, then minimum and maximum number of one address instruction that can be formulated respectively are. So what is the minimum number of instruction that my CPU can this time support? It will be 0. Why it will be 0? Because let's say I use all the states to perform two address instruction only, right? Previously I told you in this certain scenario, I told you that 0 is not a valid answer here. I told you one should be, at least one should be there, right? At least one should be there. But here why am I telling you 0? 0 can be your answer. Why am I telling you this? Because here I was telling you because it only supports two address instruction only. There was nowhere mention about one address instruction. If it supports, they will tell you. If it supports two address instruction, that at least it has to do one operation, right? Okay, one instruction. It has to support at least one instruction. That's why here 1 was the minimum value. But here already my CPU supports two address instruction, and the opcode length here was already so there were already 254 different instructions. So minimum value here can be 0, as can be seen here, right? If I am using all the states of the two address instructions, so 0 is a possibility. 0 is a possibility. So minimum value will be 0. What about the maximum value? 0 is a possibility. I have explained you why 0 is a possibility. This particular scenario. Okay. How to compute the maximum value? So maximum value will be 2 times the actual opcode length for two address instruction. So there are total 2 unused state, correct? 2 states are unused. That means how many bits were actually taken out of the picture. So I'll just explain you very small thing. So if I have a 2-bit opcode, right? So 0 0 0 1 1 0 1 1. If they say there are 2 unused state here, that means let's say this particular 2 states, 2 opcodes are these are reserved. They will not be used. They will be used to support the one address instruction. If it is reserved, that means what? That basically means if you see here, this particular bit, right, was fixed. Correct? This particular bit was fixed. And you were only varying these 2 bits. Correct? Let's say if only I had one unused state. If I had one unused state, then you don't even have to worry, right? So if you have one unused state, so what is the actual length of your opcode in your one address instruction? So let's come back to an example. 6 bytes, right? Sorry, 6 bits. 6 bits instruction. So I will come back to my example. 1 2 3 4 5 6. So out of this, 2 will be used for address, and you are saying these 2 are reserved. So these 2 are actually my usable number of opcodes, right? So how do I calculate this? So your actual opcode length, right? Actual opcode length will be what? It will be equals to the opcode length that is this one for a one address instruction, right? For a one address instruction, what is the opcode length supposed to be? It is 4. So this is like hypothetical opcode length, that is 4, right? So 4 minus what? Minus the number of bits that are reserved, that is basically minus the opcode length for two address instruction, right? So this is the opcode length for one address instruction. Opcode length for one address instruction, and this is the opcode length for two address instruction, correct? This is the opcode length for one address instruction, this is the opcode length for two address instruction. Got it? So your actual opcode length will be, in this particular scenario, it will be 4 minus 2, right? For two address instruction, what is the opcode length? That is 2 only, correct? So this will be 4 minus 2, that is 2. Understood? So now these will vary, but these two states are already fixed, right? These two states are already fixed. Either it will be 1 1 or 1 0. So what will be your total number of, maximum number of one address instruction? It will be unused, number of unused states. Into 2 raised to power the actual opcode length. So I'm not telling you to remember the formula, I'm telling you to remember the concept. Okay, I will also not remember the formula. So let's try to do this here, right? Here let's try to, like, I hope you understand the point here, right? So what we're doing, number of unused opcodes multiplied by 2 raised to power 2. What is this 2? This 2 is basically nothing but the opcode length for two address instruction and for one address instruction, right? So this is 2 raised to power 2. So got the point? Here we will do the same thing. So for two address instruction, what is the opcode length? 8. For one address instruction, what is the opcode length? It is, so this will be 12. So this will be how much? This overall thing is 32 bits. This will be 20 bits, right? So what is the actual opcode length? Actual opcode length will be 20 minus the previous opcode length, that is 8. So this will be 12. So your actual opcode length is 12, and this 8 bits are actually fixed, and out of this 8 bits 2 are unused, other remaining are the two address instruction, right? So actual opcode length is this. So your answer will be number of unused states. How many unused state I have? 2, multiplied by 2 raised to the power of actual opcode length, that is 2 raised to power of 12, that is equals to 2 raised to power of 13, right? This I can write as 2 cube into 2 raised to power 10, that is 8 million instructions. That is nothing but 8192. Correct? So this is nothing but 8192. So yeah, I hope you understood how to do the operation, how to understand what is the maximum number of supported one address instruction that this particular CPU can support. Please again watch this. I will again explain, I will again summarize what has happened here. Okay, so what we wanted to do, we wanted to support, if my CPU supports 3 address instruction, very good. But it's not always I will need to perform an operation where I will have 3 operands. I can have 2 operands, I can have one I can have one operand. In those kind of situations, I want my CPU to support those kind of operations as well. So to do that, we run into some problem. We have to reserve few bits, few opcodes, so that my CPU can understand whether this is a 1 address instruction, 2 address instruction, 3 address instruction. Till now, I have not explained how can you support 1 address, 2 address and 3 address. What have I explained? 2 address and 1 address. So I have explained you to till 2 levels. Don't worry. Yeah, sorry. I was saying, don't worry. They will not ask you 3 levels, okay? This is already very complex. They will stop at 2 levels. Okay, don't worry. For easy, they will stop at 2 levels. So I have taught you how to convert from two address instruction to 1 address. Now can you do the same for 1 address to 0 address? So let me take an example, right? Same example. Let's say it's a 6-bit processor and it supports 1 address instruction, and I want it to support 0 address instruction as well. 0 address. So obviously we can only support the lower value, we cannot support the higher value. So if I want to support, if it supports 1 address instruction and each address is 2 bits, so this will be 2 bits and the remaining will be my opcode. So total how many different maximum number of instructions 1 address instruction it can support? 2 raised to power 4, that is 16. But of course, you have to provide at least one unused state so that it can support 0 address instruction. So out of this I will subtract 1. So then I can say it can support 15 1 address instruction if I want to provide support for 0 address instruction as well. So what is the opcode length in 0 address instruction? As the name suggests, there is no address. So this whole thing is your opcode and this whole thing is 6 bits. So what is the actual opcode length? It is 6 minus the opcode length in the previous case, that was 4. So actual opcode length is 2 only. Okay. So all these 4 bits are reserved. So let's say I reserve a state 0 0 0 0. If all these 4 bits are 0 0 0, that particular case is fixed for 0 address instruction. That particular opcode is fixed for 0 address instruction. So then I can vary only these 2 bits, right? Which will be 2 raised to power 2. So how many 0 address instruction it can support? That is 1 into 2 raised to power 2. Similarly, if instead of reserving only one state, I can reserve 2 states. If I reserve 2 states, it will support 2 into 2 raised to power 2. Okay. So yeah, I hope you understood this point. That is how we can support from 1 address instruction, we can support 0 address instruction. Okay. So yeah, that is a bullet point, that is a summary that I wanted to explain, and here are the table of results which you can understand. You just understand with one level, that's it. Okay, so here that's why the answer would be 0 0 would be the, I can support at minimum I can support 0 0 1 address instruction, right? I can support 0 minimum. Maximum value would be what? Maximum value would be the number of unused state multiplied by the 2 raised to power actual opcode length. Actual opcode length, I've already explained what is the actual opcode length. Okay, so this will be the answer of this question, option C. Now we will discuss a bit more about this instruction set architecture. We will discuss about instruction cycles. So you have learned like what is the opcode length and what are the kinds of instructions, right? Now we will understand instruction cycles as well as addressing modes. Again, very important part, and it is mentioned in the syllabus, so of course we will study it. So what does a cycle consist? So although instruction cycle is dependent on machine, it is machine dependent, it is architecture dependent. All different architectures will have different instruction cycle. What do I mean by it? So every instruction, right, will follow certain steps. Those will be repeated. That's why it is called cycle, because cycle comes back to the same position, like the wheels of a cycle comes back to the same position, right? It rotates. So every instruction will have a certain set of micro instructions that it will repeat. Then you will say, if every instruction will just repeat the same thing, then what is the difference? The difference is in the actual operation of those repeated steps, right? So let's take a step back and let's understand with an example. So you are going for GATE exam, right? You are going for GATE exam, you are preparing for GATE exam. So there is a ECE aspirant and there is a EE aspirant. There is an ECE aspirant and there is an EE aspirant. What are the steps to get a good rank in GATE examination? It is very simple. You have to first study the concept, then you have to give test series, then you will have to do revision, right? And repeat all this. So in revision something might be missed and you will again repeat, study, test series, revision, study, test series, revision. For both these aspirants it is same. But what subjects to study? So the EC guy will study EDC, communication, and so on. What will the EE aspirant study? The EE aspirant will study machines, power system, power electronics. So the overall generic statement is correct. So both of them will study test series, revision, right? But individual, like internally inside the study, there is a difference. So yeah, test series also they might have different strategy, because generally what happens, the EE paper is generally on the easier side than the EC paper. The reason being the subjects are more. Okay, although I'm not making a general statement, because 2023 paper, the paper was very difficult. So that's fine. That is fine. So here the same thing. This broader statements like fetch, decode, effective address, operand fetch, execute, these will be same, but the internal steps might be different. Okay, so each instruction will be unique in that sense. Got it? Now the second point, whatever I will discuss, this is for a generic architecture. So if nothing is mentioned, then you will assume your instruction cycle to follow these steps, and otherwise it will be mentioned in the question. Each step will be mentioned in the question. It will be given to you. Although this instruction cycle is not super important, but to understand instruction pipelining, that will be covered in the next video. This particular understanding an instruction cycle becomes a very important thing. Got it? So 3 points. First point, yes, they are same, but individually they will perform different tasks individually. Second point, this is a general instruction cycle. It may vary from architecture to architecture. Third point, it is important to, although question might not come from this directly, although you may not have to remember it, but it's better if you can. But if you don't want to, it's okay, don't remember it, but understand it. because this will be used in instruction pipelining. Okay, so let's go through them one by one. So a generic instruction cycle contains 6 steps. Fetch. What does fetch means? Fetch basically means fetch the instruction from the memory. So your instruction will be stored somewhere in the memory, right? So it will fetch it. So it will, everything is stored somewhere. Okay, in the main memory or somewhere, right? It will be stored. So we fetch the instruction, basically we move the instruction from the main memory to the CPU. So here, if you see, so what happens, and who will fetch the instruction? The program counter, because the program counter knows where the instruction is stored. Correct? Because program counter always points to the next instruction that needs to be executed by the CPU. So program counter has the details. So program counter will send uh, the address to the memory address register. I will come to that, don't worry, but let's first go through this. Okay, so we retrieve the instruction from the memory, that is called as fetch. Then we decode the instruction. So if we get a instruction 1010, what does it mean? What does the machine have to do? Who does the decoding? Your manager. Your manager, that is the control unit. Just like your manager gives you some task, he defines you some task, right? So he first understands what is required, what is the requirement, then he simplifies it, and then he explains it to you that Anish, you have to perform this, or Neha, you have to do this, right? So he simplifies it, and he tells you exactly what you need to do, what are the different steps that you need to perform. So that is what control unit will do. So this decoding is performed by the control unit, and this fetch is the instruction getting stored in the instruction register. Okay, where actually the instructions is stored, that will be executed, that will be stored, right? Then we have effective address calculation. So this effective address calculation, don't worry about it, we will learn this in addressing modes just after this. Okay, there is a thing known as effective address calculation, don't worry about this, we will learn this just after this topic, instruction cycle. Okay, there is this thing. Then we have execute. So if I'm saying add R1 R2, ultimately after decoding, after all this, then finally at this 5th point we actually execute the instruction, and the 6th and the last step is write back. So whatever results you got from executing the instruction, that is stored in accumulator, and that value will be written back into whatever register you have to write. That will depend on the type of the instruction. Okay, got it? So this is the complete cycle. So let me show you a flow diagram here. So we have, so actually, because remember, this is important. Why? Because data path is in your syllabus. I want to go to that place. 77, this is the 76th slide, right? So if you see here, data path and control unit. So data path basically is that picture whatever I shown to you. So data path is actually in your syllabus, so you need to understand it. So let us see what is actually happening. So inside the CPU we have a lot of stuff. We have the program counter, we have the memory address register, right, where the address will be stored of that data that I want to get to the CPU. Correct? Then we have instruction register. Then we have the ignore this, right? IO address register, ignore all this. Okay. And what is this? This is the memory buffer register. So whatever address I sent, that is stored in the buffer, right? That data will be stored somewhere, right? So it is stored somewhere here, or it can be stored in the general purpose register. Not your concern. Don't worry about it. What is your concern? Your concern is program counter, memory address register, instruction register, execution unit. Don't worry about this thing. It is stored somewhere. What happens? this is the first step. When I say I want to fetch the instruction, I say go into the location that is pointed by program counter. Let's say currently the program counter is pointing 100. So I will go into this location 100, and here there will be some instruction that is stored in the main memory, and then this instruction goes into the instruction register. Okay, so what is happening? Program counter, it has 100. So I will go, so this 100 will be sent to the memory address register, and then the memory address register will go into this 100 location where instruction is stored, and this instruction will be directly copied into the instruction register of the CPU. After that, what happens? After that, you see there is decode. So after we reach the instruction register, then the task of control unit comes. So control unit then decodes the instruction. What does the instruction mean? And then it sends the control signal. Okay, control signal to everyone. It sends the control signal to the execution unit, obviously, and to other places as well. It will send the control signal to the memory address register. Why? Let's say if I want to perform at R1 R2, or let's say at 100 M 100 and M 200. Okay, so M100 and M200, right? So what does it mean? Going to the memory location pointed by 100 and going to memory location pointed by 200. Okay, in this case 100 is a instruction, so let us not take 100, let us take some other value. Let us take 300. Correct? So go into the memory location 300, go into the memory location 200, and then add those two values. So somewhere here in 200 I will have the data, somewhere here in 300 I will have the data. So this data actually is stored in the memory buffer register. So these addresses will be stored in the memory address register, and the data will be stored in the memory buffer register. It's not like your memory buffer register is a single register, it will be multiple registers. Okay, multiple bytes of data. Okay, so it can store multiple data. It's not like it will only be able to store single data, depends on the storage and the architecture. So after it receives all this data, right, so that is my decode cycle that is done. Then this effective address calculation happens. This happens in this phase only, memory address and memory buffer register. Then after this we fetch the operand, right, that I was talking about. So when after doing the effective address calculation that will be discussed later, then we do the memory buffer, like then we do the operand fetch. So all this data is fetched into the buffer register. This is the point. Okay, before this decode was there, and this third point. For then finally after fetching the operands, then finally we perform the operation execution unit, right? We execute. So this is called as execute, and after doing this we write back the result somewhere, wherever you want to write back, depends on the architecture and the instruction. So I hope you have understood this part. Now let's exactly understand what happens in a fetch cycle. In a fetch cycle, we retrieve the instruction that is pointed by the program counter, right, to the instruction register. Also, we increment the value of program counter. So in fetch cycle, two things happen. We fetch the instruction to program counter, and the program counter is incremented by 1. Got it? So these are the two things that happen. Okay, after fetching the instruction. And after this, the decode happens. Okay. So in the fetch cycle, what happens? This thing happens. Fetching the instruction and increment the program counter by 1. In execute cycle, so we can divide this 5 steps, right, 6 steps, like into groups. So this fetch is the fetch cycle. This execute cycle I can combine in decode and execute. Okay, where we decode the instruction and execute the instruction. So we can combine it into a simple thing called as execute cycle. And there is a third cycle that is known as interrupt cycle. What does interrupt mean? Interrupt basically means there will be a signal. Okay, that will be constantly checked. If at any point of execution of the instruction this interrupt signal goes high, my CPU or my execution unit EU will stop execution. It will directly skip it and directly go into the next instruction. So as the name suggests, it literally interrupted my execution. Okay, if you can see, if an interrupt is detected, the processor pushes the current program counter value onto the stack and control is transferred to the interrupt service routine. What does it mean? So although I told you that it will skip its current instruction and it will move on to the next instruction. And what is the next instruction? That is decided by the interrupt service routine. I will explain. So okay, let's understand what is interrupt cycle. Okay, what is interrupt? So let's say you have your manager, right? I'm taking the example of manager too much. Maybe someday my manager will give me now something. Okay, so you have your manager and your manager has assigned you some task. Okay, so let's say this is task 1. Now what happens? The manager of manager, that is senior manager, tells you to perform a different task 2, that he tells you this is more urgent. What will you do? You will say, okay, this task is more urgent. So first you will tell your manager that senior manager has come and senior manager wants me to do this task 2 and tells this is very important and this is very urgent. So I will service this first, I will do this first, then I will do the task 1. Okay, so that is what is happening over here as well. So interrupt is the owner of owner. I do agree, control unit is the owner. Okay, but if some interrupt comes, basically if some signal goes high, then the CPU will say, okay, I am executing this current instruction, but a higher priority task has came up. So I will pause my execution. I will store the current value, whatever execution I'm doing, program counter value, to a stack. So let's say program counter right now is pointing to 100. So this will be stored into the stack. And then what will happen? Then I will service the interrupt. So interrupt might say that your next instruction, don't take it from program counter, take it from the instruction that is stored in main memory at location 200. Okay, so I will not go into 100, I will go into 200 to fetch the next instruction. Now you might have bit of doubt, sir, what will happen to the interrupt if it comes in any of these cycles, in the fetch cycle or the execute cycle or the interrupt cycle? Okay, so in which cycle the interrupt will be serviced? That might be a doubt in your mind. So let me take another example. So you have an exam next week and you are practicing questions. You are solving 20 questions of maths, right? And you were solving the 16th questions and you almost got your answer. You had to find some gradient of phi. Phi is a scalar function, correct? You have to do the gradient of phi, and you just have to put the value of x, y, and z. And while you are doing it, at the same point your father came and your father is telling you to close or go to market and buy medicines for him, his medicines, right? Buy meds. So when will you leave? Will you leave before completing the 16th question or after completing the 16th question? Of course, you will complete the 16th question and then you leave. because medicines are important, but you will not leave the question in between, right? You will finish this 16 question and then you will leave, and then you will buy the medicines, and after buying the medicines you will give it to your father, and then you will continue, come back and continue with the 17th question. So if you want to leave a particular task, you don't leave it in a bad state. So we will service the interrupt only in the interrupt cycle. Only after the current execution has been done, only after the current instruction has been executed, we will service the interrupt here. So the moment I start my fetch, so what happens in a CPU? There is a fetch cycle, then there is a execution cycle, then there is a interrupt cycle, and then again, if no interrupt comes in this duration, right, again we repeat the process. So let me explain. So let's say your fetch cycle takes some duration, right? This is my fetch cycle. It takes some TF amount of time. Then you have your execution cycle, which again this time duration is variable because this depends on the type of the instruction. And then you have your interrupt cycle. So after every execution you wait a certain duration. This will be, let's say this will be fixed after executing every instruction. In this period, if the interrupt comes, in this time period, if the interrupt comes, I will service the interrupt. What does servicing means? So my PC contains the address of the next instruction, right? That will fetch. So this value, let's say 200, will be stored somewhere in the stack or somewhere. Right? This 200 will be stored. Now PC will be updated with the new instruction that will be given by the interrupt, that will be given by your master, right? So let's say this is something 300, right? So the next time I will go into the fetch cycle, the PC contains 300 and not 200. So I will fetch the instruction present in 300 memory location, I will not go to 200. So after CPU will understand, we will understand once the interrupt is finished. As soon as the interrupt will be finished, what will happen? The PC will be popped, like the stack will be popped, and that value will be stored in PC. So if I pop the stack, the value 200 will be stored in program counter, and that's it, right? And then we will continue our execution like before after servicing the interrupt. Like here, you continued solving question after giving the medicines to your father. 17, 18, 19, 20. Okay, so that is how a interrupt service routine works, and that is all you need to understand. Okay, so they can ask a basic question from this, so let's try to solve these questions. Let's try to solve this question. So consider the following program segment. For a hypothetical CPU having 3 user registers, we have 3 registers. So these are mnemonics. If you don't understand, I will explain. And don't worry, if they're asking you some question, right, they will explain what does halt, MOV, add means. Although they are very easy to understand. What does MOV, halt, all this mean, right? Okay. So let's these are the instructions, and instruction size is varying depending on the type of the instruction. If I'm doing a move instruction which has a register and memory location of 500, they're also explaining you what does this instruction do. So it means basically move the value that is stored in memory location 5000 to R1. This means move the value that is stored in memory location that is pointed by R1 to R2. Okay, so and these are the instruction sizes. What are they asking? Consider the memory is byte addressable with size 32 bits. So memory is byte addressable with size 32 bits. What does it mean? So my memory is byte addressable, right? So all your knowledge will be used. So if memory is byte addressable, so each particular cell will have 1 byte of data. Each particular cell will have 1 byte of data. Right? So let's say this is 1000 location. This will be 1001. This will be 1002. This will be 1003. This will be 1004. Consider the memory is byte addressable with 32 bits. So it is byte addressable, that we understood. It is 32 bits. What does 32 bits means? Actually, they should have properly told you that By size they mean the word size. Okay, word size is 32 bits. That means one word is equals to 4 bytes. So they should have properly mentioned. This is an old question, that's why it was not properly mentioned there. So they are mentioning instruction size in words. Okay, and okay, let's read the question. And the program has been loaded starting from the memory location 1000 decimal. Okay, so we have been loading the program in 1000 decimal. Cool. Now what are they telling me? If an interrupt occurs while the CPU has been halted after executing the halt instruction, the return address in decimal saved in the stack will be. Basically they're asking me what is the program counter value after the stack, so after the completion of the instruction, right? Because what happens when interrupt comes? When interrupt comes, the current program counter value is stored in the stack. So what is the current program counter value when it is executing the halt instruction? It is the next instruction, right? That will come sequentially after this. So what we will have to calculate? Simply the memory location that comes after this instruction. How do I calculate it? How do I calculate it? That can be calculated by understanding how much does each instruction take space. How much space does each instruction take? So if I say this first instruction, let's say this is instruction I1, this is 2 words. In bytes, how much it will be? This will be 8 bytes. So the length of the instruction is 8 bytes. So I need 8 bytes to store this instruction I1. So 1, 2, 3, 4, 5. I still need 3 bytes. So 1005, 1006 and 1007. So till 1007 only instruction I1 will be stored. Correct, till 1007. So I1 is taking 8 bytes. And if I take 8 bytes, what will be the location of the next instruction? It will be 1008, because from 1000 to 1007 I1 is stored. So how much I2 instruction is taking? The second instruction, it is one word, that is 4 bytes. So I2 is taking 4 bytes. How much I3 instruction is taking? It is 1 byte. So that is 4 byte over here. How much instruction I4 is taking? I4 is 2 bytes, which is, sorry, 2 words, that is 8 bytes. I5 is 1 byte. Correct? I5 is 1 byte. So what is the total size of the instruction? So I will explain you with a sorry, I5 is 1 word, right? Not 1 byte, sorry, 1 word, that is 4 bytes. So if the interrupt would have came after executing this instruction, what would have been stored in the stack? 1008. Correct, because the next instruction starts from 1008 location. Correct. So if, what is the length here? If the length was 8 bytes, the PC value would have been 1008. The stack counter value would have been 1008. So if the overall combination of the instructions, what is the length? 8 plus 4 plus 4, that is 16, plus 8, that is 24, plus 4, that is 28. So if the overall instruction length is 28 bytes, what is the location of the next instruction? It will be 1000 plus 28, right? That is 1028. So your program counter after, while executing the halt instruction, will point to 1028. and the interrupt comes here only. So it will complete this instruction and this program counter value will be pushed into the stack. So 1028 will be pushed into the stack. So your answer, the what is the return address in decimal, that is 1028. This value will be pushed into the stack. Okay. Now if we change this question, okay, now you will realize what is the difference between word addressable and byte addressable. If I change the question, everything is same except your memory. Okay, this, right, we should have changed this. I change your memory to word addressable. What will happen? What will happen if I change my memory to word addressable? So now each cell, okay, I don't have space here, right? So each cell will have one word. So let's say this is 1000. So this will have one word, which is 4 bytes actually. So this will be one word. This will be one word, 1001. This will be one word, 1002, and so on. So how many locations will now my instruction I1 consume? 2 locations. I1. Why? Because the length is 2 words. So for 2 words, I need 2 locations because your memory is word addressable. 2 locations. So what is the program counter value while I'm executing I1 instruction? It is 1002. What was the program counter value while I was executing I1 instruction? 1008. I hope you get the difference now. And don't worry, Gate will ask you question from this. They will ask question from this. So that is the difference, right? So now again, what is the overall word size? That is 2 plus 1 plus 1, that is 4 plus 2, 6 plus 7. So overall, how many is, like, what is the total length of the combination of the instructions till halt? It is 7 words, correct? So what is the length of I1? 2 words. So what was the PC value? 1002. What is the length of I? Combination of all the instruction? 7 words. What will be the program counter value while executing the halt instruction? It will be 1000 plus 7. That is basically 1007. Correct? So what will be the program counter value? Program counter value will be 1007. So your answer would be 1007. So that's how things can change. So every word is important. Although here they should have properly mentioned, like, the CPU works on 32 byte architecture or the word size is 32 bytes. This should be mentioned. But I hope now you understand it better. Okay, all those things. So that was the uh, end of the topic, instruction cycle and word addressing and byte addressing. Finally, if you have understood the difference, put a like in the video and comment. But if you did not understand, you can obviously dislike the video and comment that I did not understand. Okay, that is all, that is also an option for you. It's up to you if you want to understand it again by repeating the video or don't want to understand. It's up to you. Okay, so I'm giving you the option. So now we will understand what are addressing modes. So again, very important. Okay, so what happens is, I told you we have this opcode, then we have this addresses, right, through which I get the operands. Now what happens is, this address can mean a lot of things. This address can mean a lot of things. This address can be address on the memory, or it can be a effective address. What do I mean by effective address? Let's say I write this. I have this add opcode. So for addition, the opcode is 10, right? Just an example. So I write 1 0, and then in the mode I write effective or indirect. Okay, don't worry about this right now, what is indirect. And then I give an address, or let's say I don't do add, I do uh, what do I do? I do uh, I do complement. Okay, inversion. So basically, if I have 1 0 as the operand, it will invert it. It will make it 0 1. Okay. So for inversion, let's say the opcode is 1 1. Okay. And then I will provide the mode, and then I will provide the address. So this is the mode, and this is the address. Now there something interesting will happen. Let's say this address is 100, and in the mode I say indirect. Okay, indirect also will be again mapped to a certain binary number. Don't worry about it. For now, you just understand it is indirect. So what does it mean? If I say indirect, that basically means go into the memory location 100. Right? Let's say this is my memory location 100, and in memory location 100 I have 200. I will go into this memory location 100. I will see that I have 200 stored. I will not directly fetch the operand 200. No. So 200 is not my operand. After getting into the location 100, I see 200, and this 200 location is actually my operand's memory location. So again, this I will go into the memory location 200, and here whatever data will be stored, let's say 10 data is stored, and this 10 data is my operand, and I will take the complement of this 10 data. So this is what we mean by indirect addressing. What does indirect addressing means? Indirect addressing basically means that I will not directly say the address in the instruction. The address will be stored in the memory, and the address of the address will be given in the instruction. That's why it is called indirect, because I am not directly giving the address of the operand. Got it? You will say, sir, why make this so much complicated? Why do all this? There is a reason for everything. Of course, this is a crash course, one shot. I will not be able to explain everything, but this has huge advantages. Huge. You don't even realize it. This is getting used in your CPU. Okay. So we will not obviously discuss that, but this has advantages. So I do agree it is complicated, but every complication will have its own advantage, and this has its advantage. Okay. So this is what you need to understand for indirect addressing mode. So one by one I will explain what are the different addressing modes, then obviously I will tell you the definition with the help of an example. Let's take this particular scenario. Initially, let's say CPU supports the following addressing mode: immediate, direct, indirect, register indirect. I will explain all this. Then analyze the given instructions and calculate the value stored in R1 after the execution of each case. So this is case 1, case 2, case 3. If I am following this addressing mode, this one, then what will be the value stored in R1 after completing this instruction, right? So initial values are given. So register R1 contains value 0. So here I have already made a map. Register R1 contains 0, register R2 contains 50, R3 contains 200, R4 contains 90. Program counter value is 100. It is 100, and the base, there is a base register, this is called as base register, that has value 300. Okay, I will come to this, don't worry, I will explain. And these are the memory values, right? Memory location 100 has a value 300, memory location 100 has a value 300, memory location 199 has a value 100, memory location 199 has a value 100, memory location 300 has a value 20, memory location 300 has a value 20, memory location 200 has a value 40, memory location 200 has a value 40, memory location 500 has a value 60. Okay, so these are the initial states. Now let's solve one by one. So I have to do load R1 operand, and the first case is where my addressing mode is immediate mode. It is immediate and operand is 20. So what is my instruction? It is load. So the first case, load R1 20, and it is immediate. So if it is immediate, immediate means what? Fast, immediately whatever is there. So immediate addressing mode basically means immediately put this value into R1. That's it. Immediate is the simplest form. Immediate means fast. So immediately whatever is given in the instruction, put this in the R1. That is what immediate addressing means. That's it. Don't worry about anything. Whatever is there in the instruction, immediately store this value in the R1. So in the case 1, your R1 value would be, R1 register value would be 20. So your R1 register value, it will change to 20. Okay. So in the first case, R1 value would be 20. Okay. So let me put it here. First case, R1 value will now become 20 and your program counter will increase by 100 to 101 or something, right? So that will happen. So this will be 20. Let's do it for the second case. What is the addressing mode now? The addressing mode is direct mode. Direct is very simple. Direct is direct. It is not indirect, right? There is no second meaning. There is no second meaning here. It is not indirect. It is very direct. So indirect operand is 100. So again, what is your instruction? It is load R1 100, correct? And it is direct. If it is direct, what does it mean? Direct basically means don't store this value directly, but go into this memory location and store that value. That is your operand. So what is stored in memory location 100? It is 300. So in memory location 100, 300 is stored. Memory location 100, 300 is stored. So then your R1 will contain the value 300. That's it. Store this 300 value in the register R1. Direct. What is indirect? So again, here also the operand is same. It is 100 only. But in indirect, you know, they are telling you stuff indirectly, right? So it's same like your crush. So you don't tell your crush directly that I like you. Okay. So you give your crush hints. You give your crush hints like this, right? So here also there is a hint. Hint is this 100 location. So the instruction is telling your actual operand address location is stored in this memory location. Okay, very indirect. So go into this location 100, that is 300. So your actual operand is stored in 300. So I will go into 300, that is 20. So your R1 will be 20. So what about the third point? Third point is, okay, third is indirect, right? Third is done actually, yeah. Sorry, third is done. Fourth. What is fourth? Fourth is this, register mode. So register mode is very simple, R2. So if I say load R1 R2, so register mode is very simple. Whatever is the value stored in register R2, store it in R1. So R1 would be equals to R2 only, and R2 value, if you see here, R2 value was 50, right? If you see R2 value initially was 50, so R1 value also will be 50. What about the fourth case? Register indirect. So if nothing is mentioned by default, you will assume direct, right? So this is register direct. By default, it is direct only. Okay, where directly the register value is stored. Register indirect, again, there is this crush wala scene, right? So what happens here? So what we do is, I say operand is now R3. If operand is R3, what is value stored in R3? That is 200. So your operand memory location is stored in this R3 register, that is 200. So I will go to 200 location and this is my actual operand. So R3, this value is not my operand. This is my memory location where I will go and fetch my operand. So your R1 in the case 4, indirect case, would be 40, because in 200, 40 value is there. Okay. What about auto decrement mode, right? So let's take it for the first case. This is called as pre-decrement. Pre-decrement. What happens in pre-decrement? So in pre-decrement, let's do this, right? Load minus load R1 minus R3. Load R1 minus R3. What does it mean? It basically means decrement your R3 by 1. R3 value is how much? R3 value is this. That is 200. If I decrement it by 1, that will be 199, and then go into this memory location. Then go into this memory location and then get my value. So your R1 value will be memory location 199. So what is the value that is stored in 199? So your auto decrement and increment always works like that. So auto decrement and increment by default, it works by indirect mode. It works in the indirect mode. And don't worry, if some question is asked, they will be asked from this modes. Okay, these are there, but my assumption is they will not be asked. Okay, that is my assumption. They can ask, but mostly these 5 are enough, and these 5 are simple to understand. Okay, this one you will have to remember that in auto decrement mode, what happens is there can be 2 types of decrement, pre and post. I will come to that. Let's just see this. So minus R3, I will decrement my R3 by 1, and then I will go into this memory location 199. So in 199, 100 is stored. So my R1 will have the value 100. Now let's come to the part post decrement and pre decrement. So, or post increment and pre increment, right? So this is called as pre increment because the minus sign is at the starting. So here what happens, we fetch the operand after performing the decrement or increment operation. So this could have been also plus R3. Then what would have happened? I would have incremented my R3 by 1, that is, it would have become 201. Then my R1 value would have been the value stored in memory location 201. Similarly, there is post increment, post decrement. What does it mean? In this certain scenario, first I will fetch the value. So I will decrement and increment later, post, right? So what is stored in R3? 200. So I will get the operand, right? That is stored in memory location 200, and I will store it in R1. After that operation, I will perform my increment and decrement. So R3 value finally here and here. In both these cases, they are same, right? In all these cases, they are same actually. It is same. I mean, not all these cases, sorry. In case of decrement, it is always 199. In case of increment, it is always 201. But the value stored in R1 is actually different. So that depends whether it is pre increment or post decrement. Post, if it is post, then I will fetch the operands first, then I will increment or decrement. If it is pre, then I will increment or decrement first, then I will fetch. Cool. Okay, so there are a few more. Bear with me. So okay, 6 is done. Let's do it for the 7th one, right? So okay, so this was the 4th, this is okay, 7th. This, let's do it for the 7th one. This was the 6th one. Indirect mode I have already explained actually, right? Where is the indirect mode? I don't know. So we're okay, we have lost count. So this is the 4th one, this is the 5th one. Okay, so let's try to do let's try to solve it for the seventh one, that is the index mode. Okay, what will happen in the indexed mode? So in the indexed mode, you have a base register and you have a index register, which don't worry, I will explain. So the base register value is R4. So what is there in R4? R4 90. So this is the instruction, load R1 and your index register is 10, right? So load R1 10. Okay, and you might have doubts, sir, how will the CPU know that whether it is immediate mode, direct mode, indirect mode? How does the CPU know? As you said, CPU is very dumb. So if you see the first picture, right? If you see, this is my whole instruction length. Okay, I forgot to mention it at that point of time. This is my whole instruction length. Now what happens is, in this instruction length, some of it is used in opcode, and this particular length, right, is used to define the mode. Mode 1. What does mode 1 mean? Mode 1 defines the addressing mode of address 1, whether it will be immediate, direct, indirect, register. This mode 1 bits will decide. Mode 2 will decide the addressing mode for operand 2, that is address 2. Got it? Cool. So everything is defined. So yeah, so what happens is, load R1 10. So your base register value is R4, which is 90, right? R4 is 90. If you see here, R4 is 90. Correct? Just give me a second. Yeah, R4 is 90. Right? So R4 is 90. So what will be the address of your operand? So in case of index addressing mode, the address of your operand will be computed by the base register value plus the index, that is 10. So this will be the location. So that is 100 in this case. So your operand value will be what? The value that is stored in memory location 100. What is stored in memory location 100? It is 300. So your R1 value will be 300. Do you have to remember it? Yes. Do I expect a question getting asked from it? Maybe. Is it very difficult? I don't think. But there are so many subjects, you might forget it. So you will have to revise it. That's it. Got it? Then you have PC relative mode. In PC relative mode, basically the same thing, right? Similar thing. Just the difference is your base value, right? Load R1 300. If it is PC relative, right? That is the instruction. R1 300. Sorry, 400 basically. R1 plus 400. This will be equals to what? The PC value plus 400. PC value is how much? PC value is, what is the program counter value? Program counter value is 100. So 100 plus 400, that is 500. So the address of your operand is actually 500. So what will be the R1 value? It is the memory. It is the value stored in the memory location 500. So what is stored in 500? 60. So your R1 value is 60. Okay, let's do the last one. After that, we will be done. So this one, right? Base register mode. In base register mode, what happens is basically whatever is the value stored in base register, that works as base. That is the only difference. Okay, that is the only difference. Okay. Yes. So I think the instruction also changes, if I remember it correctly. I'm just trying to think. In base addressing mode, yeah, no, I don't think it changes. So now if I write here, load R1 minus 100, load R1 minus 100. So what does it mean? If it follows the this addressing mode, that is base register mode, it basically means that go into the base register, that will be your base address 300. So 300, and this will be your index. So 300 plus index is what? Minus 100. This is 200, right? So your R1 value will be the value stored in memory location 200. So what is stored in 200? 40. So your R1 value would be 40. Okay, and you're done. Okay, I think we're done. Okay, this will be 7. I'm just running out. I'm just forgetting to increment, right? This will be 8, and this will be 9. Okay, so yeah, you're done. So those are the addressing modes. Again, I have told you which ones to remember, which ones you don't need to remember, and this is a summary. Okay, if you see in immediate, what was the effective address? Effective address basically means the address of the operand. It was nothing because you directly provided the operand. It was 20, if you remember in the case 1. You directly provided 20, right? So your R1 value was 20. So how many memory access you required? None, because the operand was given to you in the instruction itself. Direct mode, the effective address was 100. How? If you see here, right, load R1 100, where 100 is the, if as it is direct, where 100 is the location of the operand, right? So that's why 100 is the effective address. 100 is the effective address, and your operand was actually 300, right? If you see here, the operand was 300, R1 value was 300. How many memory access you require? 1. So these are all important actually, because the more memory access you will require, the longer it will take, because the main memory is slower than the CPU. Although it is fast, I agree it is fast, but it is not as fast as the CPU. Okay, so yeah, now that's it. So you will need one memory access. So you will say, why will I use this? I will use this. This has its advantage. Okay, this has the advantage of modularity. So yeah, that is a separate topic. Now what about the indirect mode? In indirect mode, if you see, what is your effective address? Effective address is the address of the operand. So this is not the address of the operand, right? You have to go into 100 location. Go into 100 location. If I go into 100 location, I see 300. So this is your effective address, and your operand is 20. Correct? So 300 is your effective address, and your operand is 20. How many memory access? 2, because the first memory access was actually required to find out the effective address, and then another memory access to actually fetch the operand. Similarly, you can see, like, for all this, you can see and summarize. I will not bore you. You can see the table and do it. Okay, so there are definitions that are written for each of them, all because I have already explained you what does each operating mode, each addressing mode does. So you can pause the video, read, pause the video, read, pause the video, read, do it. Okay, read. I've already explained everything, mostly everything. So if you have any doubts, you can go and have a read on this, what does each addressing mode does and how it does, right? Okay, so here I was explaining. So register indirect mode, it is faster. So what happens if we are using register addressing mode, right? Because register is stored in the CPU, general purpose registers. So those are actually very fast. So if I am using register addressing mode, that will be faster than direct addressing mode. Okay, if I am using register indirect mode and I compare it with indirect mode, which one will be faster? Register indirect. Why? Here also there are two memory access, here also there are two memory access, but one of the memory access here is register access, which is fast. Okay, that is what I have explained over here, and there are many advantages. You can go and read what are the advantages and stuff. I will not go, like, I will not explain you, because not super important. Your task is to solve the questions. So I have told you how to solve the questions. So we obviously, for that, we will take questions. Okay, we will solve questions, don't worry. So yeah, I will come to the questions directly, because you can go, like, you can go and have a read. I will try to provide the notes, don't worry. I will provide the notes. If there is enough demand, I will provide the notes. So for you, you can pause the video, right? You can here pause the video and read everything. So this was the part you can pause the video. This is the part you can pause the video. You can pause it here. You can pause it here, read exactly how each addressing mode occurs, but I've already explained it. Okay, this is the part. This is the part. So you can read all this already. These things I've already explained you. Okay. Okay. I think that's it. So branching I will not explain for now. Branching I will explain in the next stuff. Okay, don't worry. So this branching will be explained in the next pipelining lecture. Don't worry about it. Okay, I want to come to the questions. These are the advantages and disadvantages. So let's do few questions. That is the important part. Okay. So this is the first one. Try the questions by yourself. Whatever you have learned now till now, try the questions by yourself. In which of the addressing modes is the operand not included as the part of the instruction? So operand is included as part of instruction in which kind of addressing mode? Immediate addressing mode. Other than that, is ever your operand included in the part of the instruction? No, right? Only in immediate addressing mode, the operand directly is included in the instruction. Otherwise, you will always have to do some memory access or go into some general purpose register. So in direct addressing mode, operand is not included. Indirect, not included. Register also not included as a part of the instruction. Okay. So option B, C, D will be the answer of the question. Let's solve this one. The most appropriate matching for the following pairs. Indirect addressing modes. Okay. This one actually you can skip. Okay. This one will not be asked, because this is a coding kind of question which I know you will not be able to understand. Skip it. Okay, this one also you skip it, right? Because this is a C++, this will not be asked. Skip it, because these are C++ questions. So till now, whatever questions you are solving, right, except the easy ones, obviously, those were CS questions. I have not told you because I don't want you to get scared. Because what will examiners do? They will also take some questions, right? They will also take questions from somewhere. So obviously CS already has the subject COA. From there only some questions will be filtered out that will be catered towards your examination and asked, right? So don't worry, and you are able to solve the CS questions. So but I will obviously choose those questions only that will be asked in your examination. Otherwise I will ignore those, because I deleted those previous two questions because those are not relevant for your examination, for your subject. Okay, for your paper. That's why I deleted it. In the absolute addressing mode, the operand is inside the instruction. Is it? So absolute, what does absolute addressing mode means? So absolute is also sometimes called as direct. Okay, so these names are very bit confusing, I do agree, but you will have to remember it. Direct. So in direct addressing mode, the operand is inside the instruction. No, that happens in immediate, right? This happens in immediate. The address of the operand is inside the instruction. Yes, that this should be is actually. The address of the operand is inside the instruction. Yes. The register containing the address of the operand is specified inside the instruction. No. This is register indirect. Right? Register indirect. So this again you don't have to worry about it. But if I want to explain, so here what happens, the location of the operand is implicit. Basically, it is already inside the opcode itself. Okay, the location of the operand is directly present in the opcode itself, not in some address 1 and address 2. So again, not important, ignore this. Okay, so what is important? Direct, indirect, immediate, register direct, register indirect. Okay, so option B will be the closest one, although this is a very old CS question 2002, right? There properly things were not mentioned. That's why they should have mentioned what do they mean by implicit and stuff. It was not mentioned. That's why there might be a bit of confusion. But this is direct addressing mode. Okay, so now let's come to the actual question that came in your GATE examination, right? GATE EC 2024. And almost whatever you have learned till now, all those concepts will be used. So it's not like I'm teaching you something that will not be used. Everything will be used. Everything will be asked, right? So a machine has 32-bit architecture with 1 word long instructions. What does it mean? So one word, it uses 32-bit architecture. So 1 word will be equals to 4 bytes. Correct? And it has 1 word long instruction. So the instruction length is 4 bytes. That is basically 32 bits. It has 24 registers. So 24 registers. So from R0 till R23, and supports an instruction set of size 40. So there are how many instructions? Total instructions there are 40. Each instruction has 5 distinct fields. Each instruction has 5 distinct fields. Correct? So, okay, this is my instruction, and we have 5 distinct fields, namely opcode. So the first part is opcode. The second part is two source register identifiers. So there will be two source registers. Let's say this source register 1 and source register 2. Basically, from where I will get the operands. These are the sources. And what is the next? Last one is one destination register identifier. Okay, destination register identifier, where basically the result will be stored, something like that. Correct? And the last one is an immediate value. Immediate value IV. Okay, assuming that the immediate operand is an unsigned integer. This is an unsigned integer. What is the maximum value? So if your immediate value is n bits of size, do you know what is the largest value of an unsigned integer? If my immediate value is 2 bits larger, so what is the maximum value? It is 1, right? That is 3. That is 2 raised to power 2 minus 1. This has been taught to you in digital electronics, that how to compute the maximum value of an unsigned integer if it is n bits. So here it will be 2 raised to power n minus 1. That is what you have to calculate. For that I need n. How do I calculate n? So how many different instructions does my machine support? 40. How many bits do I need in the opcode? 2 raised to power 6. I need 6 bits, right? 6 bits can actually make 64 different instructions. I am not using 24. I cannot use 5. If I use 5 bits, I can only use 32 different instructions. If I use 5 bits, I can only use 32 different instructions. If I use 6 bits, I can use 64 different instructions, out of which I am only using 40. 24 are getting unused. So the size of the opcode will be how much? How many bits? This will be 6 bits. What will be the size of the registers? Register address. There are total 24 registers. How many bits do I need to define 24 registers? Log base 2 of 24. Again the upper limit. What is this? I need 5 bits, right? Because there are 24. Although with 5 bits I can define 32 registers, but we are not using all of them, so that's fine. So each register will have 5 bits. Each register address will be 5 bits long. So overall this is how much? This total is how many bits? It is 15 plus 6, that is 21 bits, plus x or n, right? N bits for the immediate value will be equals to the total instruction size. That is how much? That is 32 bits. So this will be equals to 32. So your immediate value size will be 11 bits. So what is the maximum number or the largest number? That is 2 raised to power 11 minus 1. That is 2048 minus 1, that is 2047. And this is your answer. And this came for 2 marks. 2 marks or 1 marks, I don't remember. Okay. But the previous question actually came for 2 marks. That easy one. So the solution was very simple, right? Not simple actually, solution was very small. But there were a lot of things that went into it, right? We had to build a lot of foundations. If you are able to understand this solution, then congrats, this lecture was a success. Okay. If you are not able to understand it, then that's my failure, that I was not able to explain to you properly, because they are asking good questions. Although they have asked questions rarely, but I'm expecting one day they will ask 1, 2 questions or 3 questions, right, from COA. And that day you will be able to solve, because we have covered everything from basics and we have learned everything, right? So that day will come, obviously one day will come, because it is mentioned in the syllabus. If it is mentioned in the syllabus, they will ask. Now when they will ask, we don't know. So whatever I have taught to you, all those knowledge will be used here to solve this, right? If I directly had given you this question and directly would have explained you the solution, you would have never understood the solution if you would not have gone through the lecture, right? So we had to build up a base here. So yeah, I had taken few additional questions as well, so that you can understand those parts as well, right? So I hope you understand this lecture. If you did enjoy this lecture, right, and if whatever I have taught to you is clear, drop a like and drop a comment. That will help me out a lot. That will motivate me to provide the second part. Okay. So second part will only come, and you will get the notes of this lecture only if you provide good support in this lecture, right? So it's almost around 2 a.m. right now, and I'm recording for you guys because I know exam is near, and COA, although it has been asked for lesser marks, but if someone wants to cover it in 3-4 hours, they can cover it and they can gain 2 marks from it, right? 4 hours, 2 marks. So if you want the second part to come, that is the remaining portion, that is instruction pipelining, right, and data path, bit about data path. So that will come only if you provide enough support in this video by liking, and you can share it in your WhatsApp status or groups, and by commenting. Okay, if you have understood the questions and everything, you can comment whatever you felt like in the lecture. Okay, so that is my demand. If that demand is completed, I will bring the part 2. Otherwise, part 1 will be the last video, okay, for COA. So it's up to you, and yeah, I will see you in the next lecture. Until then, happy learning.